రైట్ ఒకవేళ ఇట్లా దాని దాడదిలో రికార్డింగ్ పెట్టారు ఒకరికి మళ్ళీ దేశంలో పడేద్దాం. హలో 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 నా మైక్ ఆఫ్ చేసుకోవాలి. Hello, 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 hello. Hello, 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 hello. Ready? Connect.
You can get started.
So, Professor, we are starting with examples.
Right. I mean, we'll go back later for the 2A slab theoretical part, but that's later. For today, before they all get tremendously bored about all the theory, we will look at these are fairly very simple example, but I'll try to mix and match the examples with the theory part of it. Perhaps if you can turn that thing on. Yeah. Thanks. Any questions broadly speaking, in terms of yesterday's discussions? No. Okay. What I would like to start out, of course, one of the small disadvantage we have today while running these examples is I haven't said a whole lot about serviceability so far. I mean, I wanted to cover that. I still have a few more slides to cover, but I did not cover. I'll go back and cover after doing a few examples, So we're putting the horse behind the cart for today, a little bit. But what I want to say is that I have not also covered the concept about the moment of inertia in its gross value, I gross, I cracking, and I effective. So people have to really understand that carefully before we can even talk about a design that would be checked against serviceability. Unfortunately, serviceability is the primary issue, primary design controlling issue here, unlike in steel. And another thing, if you are dealing with tension failure, the equation to Mn is relatively simple if you are dealing with a tension failure, but it gets a little bit, not a whole lot, bit more involved if we are dealing with a compression failure. That is where that equation with that square root of a thing comes into picture. So what I want to do, I know this is, for some of you, maybe this is fairly sophomoric aspect of it, but I will try to keep it as simple as I can. That is the strain compatibility. In this case, if you call it FRP, we said it is 0, 1. Right? So, if the strain is let's start with the compression failure, because the tension failure stuff is extraordinarily simple. So when we say it's a tension failure, I said just now, extraordinarily simple. So when we say it is a tension failure, what are we saying? You have this is predetermined, right? If it's a tension failure, it's already predetermined, like 0.01 times modulus times of the GFRP. So that's predetermined. So this number is 0.01. Young's modulus is also predetermined in a way, or given for FRP, which is times the A of FRP. That's what I mean by predetermined. So Mn, I cannot go right in big hurry, is all jumbled up, so I'm going to write it slowly. So if this number, let's say, it's going to be given to you anyway, if this number is say 6 million psi type modulus, so this automatically becomes, as I told you yesterday, 60,000. This times this. And then this is AFRP. And then you multiply that with the D minus A over 2. This is this is A. Okay. So D minus A over 2, your neutral axis is somewhere here. This is, that's not D1. So that is the neutral axis. And we can easily find A from force equilibrium. So you see what I mean? Therefore, you do not have to solve this as a quadratic equation. That is the advantage of, you know what a lot of people do? A lot of people would even simply say, I have accurate. That's what people do. A lot of, because we have many other factors of safety. Now it doesn't matter whether I'm talking this D minus aorta is 0.9D or 0.85D. It's going to hover around that number anyway. You know, you follow how a designer thinks. A good designer doesn't really rely heavily on minute number crunching. He or she always looking for a farmer's approach. I'm going to spit in the air, see which direction the wind is blowing. You know, that's a good design. So they normally, instead of going through the force equilibrium and getting this, they would simply say 0.9, 0.85. You know, for steel it may be 0.85, 82. For composite it's probably 0.992, simply because of the smaller. If you really, I don't know how many of you observed it, in a tension failure, not compression failure, in a tension failure, the depth of the neutral axis at failure, uncracked part before it crushes is about 0.8. So people say, for all practical purposes, it is about 10%, you know, 8 to 10%. That's what the people say. From a designer point of view, mind you, remember, or else if I had to go through all the equilibrium aspects and what, I'll go to this, and then I'll substitute it in here. But from a designer, this is more than adequate. That's the thing. So there is no, my message here is, there is no quadratic equation there. Now, on the other hand, if I go to compression failure, I will get into the quadratic equation issue. How is that? So this is the lowercase c. We are saying it's a compression failure, right? Therefore, what does that mean? This is going to be 0, 0, 3 or 3, 5 or 4, depending on the code. As if Professor Prakash is saying, if I use fiber concrete, that could very well be 0.005 or 6, in that range, you see. So from that, I'm going to fix this. So this is no longer that. So the tension, the strain value in tension is going to be epsilon Cu, which is 003, right? That is that. Multiply that with D minus C by C, right? Then that is the compatibility. This is what we call strain compatibility. So then this is, in an approximate sense, so
maybe you could do the other one. The one that.
So this is AFRP times FFRP and FFRP is, this is the one. That is the strain, you multiply it with 6 or whatever, EFRP. So, this should be equal to this, that is the equilibrium part of it, and you substitute, from this equilibrium, we are now trying to find C, which turns out to be a quadratic equation to find C. Once I know C, the equation for M is essentially going to be the same, except you are going to look at it from the standpoint of, whatever that 0.85. F prime C. It's not writing well.
Yeah, I think there is some, we can write, yeah, the anti-touch or something, you have to remove that. That's okay, I should do something. You can go to the pen, yeah.
Maybe it's
You put the hand, it is touching, so
Right.
we have to remove that. How do we instead of the hand touch, we have to remove that.
seconds.
Multi-finger, only this, yes. Now you just a little bit, go back. Yeah.
Seconds.
Only this, only the eraser.
That is locked.
Locked, right? Yeah. Because while touching, it's
Yeah. Well, also it's not writing well.
yeah, it's not right.
Yeah.
Yesterday it was okay. Just call Vijay.
Okay.
It is touching.
That's what we should.
Okay. Let me see if I can do it without touching it. So anyway, the message is that the forces 0.85 F prime C, that is the stress, B times A, which is beta 1 C, and that is equal to A of FRP times 0.003 times B minus C over C times E of FRP. So now with this equation, you are trying to solve for C, which is a quadratic equation. That is where you got that square root business and what have you. You follow me?
Sir.
This is a very, we learned this in, as soon as you get into structural engineering, concrete, you learn that very first thing. So that is what we had. Once you have the C value or A value, you can find the bending moment value. All right. Now, keeping that, the reason I say that is because today in our examples, very, very simple example, hopefully I can cover 8 or 10 today, maybe 4 or 5 tomorrow, because the ones tomorrow are more involved, the 10 are fairly rudimentary. The reason I'm even putting this here today, I'm going to use some of this in the example. That's why I even brought this up. So, I don't know why it didn't print. That is a 12-inch by, okay, this is a compression-controlled section. And this is a rectangular section, 12-inch by 20-inch section with a cover of 2.5 inches. So the strength reduction factor, somebody was asking me yesterday, for compression is given right there. That is the strength reduction factor. So how do we know that this is leading to be a compression? That's the first question. How do you know? Anyway, before we go there, what we typically do as a starting point in the design of a bending member with steel reinforcement is you start with approximately 1% for beam bending with steel as the amount of steel, 1% of the cross-sectional area B times D. D is the effective value. That's just a guide, remember. It doesn't have, it could be 1.25%, it could be 0.8%, but that's for beam bending. For columns, we use approximately 2 to 3%, but we can go sometimes for high-rise building columns, we go up to 8%. On an average, that's the highest. The code clearly says don't exceed 8%. But on an average, we use more like 4 to 5%, which is still slightly higher, but you can go safely to that level. I would use 2 to 3% to begin with if it works. Another thing, in steel we like to tell the students is that make an attempt, if your design fails due to the fact that not able to satisfy the moment requirement, first thing we want them to do is increase the area of steel. The second thing is increase the strength of the concrete. So these are the immediate, don't dabble, if you can help it, of course. All these are if you can help it. Don't dabble with the cross section to start with. Try these two first. So we keep that philosophy in mind. And now, that's for steel, that 1%. For FRP, we may be talking about 2 to 3%, especially when you are talking about compression failure. If it is a tension failure, we initiate the discussion with 1.5%. Okay, if it's of course, tension failure has a penalty. We talked about it theoretically, but that is in that range. You have tension failure around 1.5, less than 2. Whereas a compression failure is about 2.5, 3%. You may get there. Okay, those are the broad parameters before you initiate a design. Okay, now there was a typographical error that is not 7, it is 17.5. B times D. B is 12, that is 17.5. So what did I say? I want to make sure for this given cross section, we have 4 number 8 bars, and the number 8 means 1 inch diameter bar. It is 0.79 square inches area, so 0.79 times 4 is 3.16. That is the area of FRP. And the rho F, the rho implies that is the what percent? Here you see 1.5% of the cross-sectional area. When I say cross-sectional area, is the effective cross-sectional area, not the total area, not the cap D, but lowercase d value. Okay. Now, what is rho FB? That's why I put this thing up. So, how did I get this? It comes from here. Okay. That is from the compatibility issue. Strain compatibility, you're correct. Now, if you don't know how I derived that, it's all in there if you look at it, but I'll be very happy to provide you with additional intermediate steps if you, so, but this comes from the strain compatibility. Okay, that's a very, very important thing because that determines whether a given section is in compression or tension failure. So in this case, as you can see, rho FB is 0.01, whereas we have provided 0.15. Obviously, it is a compression failure. So that is the first step one must arrive at. Is that clear? So if it is a compression failure, we are talking about 0.65. Tension failure, it is 0.55. So when I say it is a compression failure, that's why I went to the black, that whatever your green board there, and now I'm trying to find the stress in the FRP rebar. And that equation, you have that equation. I gave you that equation in your earlier slides, and you substitute it in there. And I said this before, I'll repeat it. This component is negligible, really, compared to this component of that equation. So really, you can get away, that is what? That is 324 divided by 4, that's 81, and this is a much higher value than that, so you can neglect that pretty much. If you do, again, if you don't know how I arrived at it, I described how to arrive at it. If you don't know it, please let me know. So we found the stress under the compression mode of failure, which is a function of 0.003, and as Dr. Prakash was talking about, if this number ECU is 0.4 or 5, 004, 0.006 or whatever, then obviously this is going to shoot up. So that is the advantage you have by having a higher strain to failure in compression. At any rate, so the A value, where is this coming from? This is strictly coming from equilibrium equation. ASFF is the force on the tension side, 0.85 F prime C B A is the force on the compression side. Therefore, we got a value. A is different from C. So the neutral axis from American code point of view, this is the neutral axis depth, whereas A for a rectangular equivalent idealized rectangular stress block point of view, A is beta 1 C, whereas beta 1, I told you, varies depending on the strength of the material. The reason they cut off in ACI at 8,000 and they said above that it is still 0.65, because for some reason we feel 8,000 is a cutoff limit for regular concrete versus high strength concrete. So the code here, I didn't mention that emphatically, is only valid for regular concrete. Code is not calling for higher strength concrete. But I really like this concept about increasing the strain value using fiber. Yeah, that will help a lot from an economics point of view. But maybe you know better than I do. Why it didn't catch on, the fiber concrete in US, I do not know. But very few people, as a structural concrete, we do that fiber concrete all the time for basements, for sidewalks, for driveways, we do that all that. But it never caught on. My very good friend, Suru Shah, worked his whole life on that. One of these days, I can't resist with asking, why the hell you didn't get this going anywhere? I don't know why, do you know?
I think the major issue is, to get really steel-free concrete, you end up putting high volume dose fibers. When you want to put like upwards of 1.5–2%, the mixing becomes
So it doesn't exfoliate.
balling
Right.
effect. The balling effect.
Okay.
On
Yeah.
top of that, again, anyway, you will end up putting some steel wheels because here you are dispersing the entire medium. So it helps in ductility, but in steel, you are lumping everything at the location where you want in tension. So you end up with more economical sections when you have regular.
So you use, when you say fiber here in this country, you use mostly steel fibers?
Steel.
We normally don't use steel fibers. We only use polypropylene, polyethylene type fibers.
There are two varieties.
Uh-huh.
There is a microfiber, which we use for shrinkage, which are typically less than 0.2 millimeter, the short fibers.
Uh-huh.
And then we have macrofibers, which are typically more than 0.2 millimeter in diameter, longer. So the synthetic fibers about last macro synthetic fibers, which are structural for structural crack, they are available for last I would say 5 years, 10 years. So now increasingly being used in India. They are more flexible, malleable, so you can mix it very well in concrete. But the efficiency of crack arresting is less because the stiffness is less. So now people are using both steel as well as this. Again, steel also now again microfibers are available, which are again easy to mix in special concrete. But again, the cost. For example, slab on grade, as you said correctly, here also a lot of industrial flooring they do with steel and synthetic fibers, but they are, I don't know, somehow still there are a lot of resistance.
Yeah, it didn't catch on. There's a huge amount of funding given for 20 years in US, but it just didn't, structurally nobody is really using it, to be honest. On grade, yes, they're using it, no doubt. But structurally not able to, I really need to know why. But another important thing is the sizing issue. You see, people, what happens is industry guys take it onto themselves, don't fully understand the science, and then they want to use it. The balling effect comes because there is no appropriate sizing on the fibers. If you have this sizing, it can exfoliate much easier. The dispersion becomes more uniform. So maybe that is another area that one needs to be working on, But that definitely has a lot of potential. If Bazant worked on that from a theoretical point of view, and Suru Shah did that from experimental point of view. Okay, but that's where we are on the microfiber type thing. Okay, so once we know, you understand the A comes from the equilibrium, and now it doesn't matter whether the nominal value is obtained with a force function from the tension side or the compression side, because they're both are equal. AFFF is equal to that, so it makes no difference. So that is this is the nominal moment, we call it. Now I'm talking, analysis part is pretty much over. Now I'm going to talk about how we compare it as a designer. So Mn is a nominal moment. Phi is the reduction factor from the material point of view and also from the point of the failure mode. That's the phi value. So your ultimate moment, including the load factor. So in my next day or two, when I say load factor, load related moment, we call it, implying that includes your load factor. So keep your, that slide where I gave you on the load combination, keep that slide in mind or keep it open, because we will be using that. So the message here is the following, that this number should be higher than M sub U with the load factors. That's about all is there with reference to bending design in a compression mode. So any questions now? Anything on that? So I don't see. But the tension mode of failure I'll be talking about in the next example is much, much simpler because you don't have to even worry about that quadratic equation type thing. If it is a tension control, all I have done was I took the same cross section and I reduced number 8 bar down to number 5 bar. Say, so that the thought process would be streamlined, focused on area of steel rather than something else. So if you look at it, again the same drill, right? No big deal. So you have 17.5, the rho F is 1.24, so the number 5 bar is 0.6, 0.3 I mean, so you get that 1.24, 4 times 0.31. Anyway, the rho F is as given the equation, we gave you the equation again coming from that compatibility and you can see less than 1. Right. That's what it is. Therefore, the phi factor is 0.55. So yeah. So this is how we dumb it down. So these are very rudimentary examples. When I go to the design of a two-way slab, you will see the complexities, That's why I kept it to the last. I'll take a couple of hours to run the whole example. It has many, many steps and many, many slides with it. Okay. All right. So we talked about, is that clear? What is a compression control? What is a tension control? Okay. So what are we learning here? Phi factor is different, number 1. And the rho versus rho F, rho higher than rho F is compression, rho less than rho F, tension. So now all we are showing you there is how to find the phi times mn. Okay. You can see that is mn, multiply that with the phi, that is in inch cubes. And the C for the balance is given to you there. That's a very standard equation. This is the force, AF, FFU is the force, that is the lever arm. So A over 2, what is A? 0.85 times C. So, okay, the difference in terms of tension control and the compression control, I told you that yesterday, I don't know how much you caught on to it, is the minimum value of reinforcement. That is if you're going to design it as a tension failure system, you must, why that is given there. Where that is coming from. You may not know how to derive that equation. You know where it's coming from? It is coming from, we equate the first crack moment that must be resisted by the reinforcement. And that's how we arrive at that minimum, so that when it has a very first crack, it's not going to have a catastrophic failure. It will be held on together before it meaning the crack opens up. That is my emphasis. This is a B sub W. That means whatever the effective width or whatever, even for the T sections and so on. So at any rate, the AF min is 0.96. So if you remember in the same example in the previous slide, we provided 1.24. So we are satisfied we have satisfied the minimum requirement. Okay, here, there it is, 1.24. So this is an extra check compared to the compression failure.
In this case, that 5 ml, that must be equal to ultimate moment or
Ultimate, okay.
ultimate moment.
This, please note, this moment, phi times ml, must be always higher,
Higher than
m sub u.
then
That m sub u is, you will see that in when I run this, I call this an analysis problem. You will see that in a design problem, that m sub u is inclusive of your load factors. Not only that, you have to go through combination 1, combination 2, combination 3, 4, 5. That's why you keep that chart in your mind. So anyway, the straight answer to your question is phi mn should be larger than m sub u of different load combinations inclusive of the load factors. That is the answer to your question. I'm trying to look what slide number I have that. It's, I think, 105 or something like that. But at any rate, yeah, I told you, I alerted you several times that you need to keep that slide in your mind. What slide number? That slide,
96.
96, okay. So that slide number 96,
yes.
oh, you opened it. Okay, thank you. So you can see, I want to keep repeating that. That's slide number 96. So we have to check for all these load combinations. 1.4, only dead load. So you see, the reason I want to thank you for opening it, I'm glad you opened it. The reason I want to go there is, why is it that it is 1.4 load factor when only dead load, 1.2 load factor when it is a combination of dead and other loads? Again, this is where what they call uncertainty of loads acting on a structure would come into the play. That is where all these concepts come into play. You see? And many dissertations were done. All this comes from field evaluation. So they go to 1,000 different slab systems, for example, and measure what is the thickness, and you say, okay, the max thickness value is 40% higher than the called for 6-inch means. Sometimes people put 8 inches, sometimes they put 5 inches. That is that bell-shaped curve. So that is where the factors were derived. Again, we have no control on this, I said. This is, we have two sides of the equation, right? One is the resistance side, which we talked about so far. The other is the load side. This comes from the load side of the equation. We cannot touch it. It comes from the ASCE 7, which calls for these kinds of load combos. Likewise, you have a lower live load, dead load combined with the live load, and you can see, because the uncertainty of live load is more than the dead load, that's why the factor is higher. So
In Indian code, we have 1.5 dead load and 1.5 live load. Both are same
yeah,
in Indian.
yeah. I don't agree with
But
that.
the uncertainty
Is higher
both
with
in
live load. That's why we did this. So that's why I said I don't necessarily agree with the. I have a tendency to speak my mind. I get into trouble, right? So, but that's what it is. Other load combinations, you can see how. Again, I'm not going to get into it because we have no control on that side of the equation. They are given to you. You don't believe it. it looks so simple. ASCE 7 on loads and load combination is this thick a book. It's about 1,200 pages. So that tells you how much work goes into it. Therefore, I'm very cautious not be too critical about it, because there's a lot of thinking went into it. You see, it's easy for me to stand here and criticize it, right? But you don't understand the other flip side of this coin, where how much work went into it, you know. Nobody takes it casually when they make a statement. So those are the kinds of checks and balances we need to make. Okay, let's get back to our okay. So, couple of things. We only talked about strength limit state. This is all a strength limit state. We didn't say a word about stiffness or other kinds of limit states. You remember the 4 limit states I gave you? So that needs to be checked, but I'm focusing only on strength for the time being, you know. So that gives you a good check. One-way slab design. This is another example. So, I'm sure most of you know what is a one-way slab versus a two-way slab design, and you see there is a lot of fascination to arrive at these slab related moments in a most high accurate manner and all that good stuff, right? I mean, mathematically sounds good, but a designer doesn't care. Therefore, what I'm trying to say is, first thing you should recognize, there is a positive moment, meaning causing tension at the bottom, and a negative moment causing tension at the top. That's positive, negative, it's a definition, right? That's why I said tension causing at the bottom and the top. So how do you recognize that? If you draw a bending moment diagram, you will see that. That's the first thing you appreciate. The second thing you should appreciate is right off the bat that approximately what they call positive moment is WL square over 16 or 17. The negative moment is WL square over 11. You know what I mean? So that is the second thing you need to recognize. And then now you're ready to design for the positive moment and negative moment. So anyway, that is how they simplified it. So we are now going to design this for both. Another interesting thing they talk about is your positive moments are lower in the interior spans compared to the exterior span. You know, again, people quibble about all these kinds of things. Ultimately, they don't matter much, really speaking. But we have to go through the motions anyway. That's what the code is calling for. But our code says, I don't know what your code says, WL square over 11 for the max negative, WL square over 17 for the max positive moments. That's an oversimplified approach. Remember that. Those are the words, oversimplified. But that works. As long as it works within a few percentage points of view, it doesn't matter, you know. All right, now, so where do we start? Again, as I indicated, for a beam, we are talking about L over 12 or something. For a slab, we are talking approximately around, this is where we start. I'm not saying that works. That we're going to start with that and cross-check whether it is working or not working. That's our next step. So this is all given, the F prime C, that is about 25 or 28 or whatever, 30 MPa. And this is given again, 90,000 PSI. It may be different, you know. I'm taking that as a pretty standard value. No.
Quick question. Sorry.
Sure, sure.
Typically, the L by D ratios that what we use for steel is on the higher side. Probably, I think, because this is governed by
Exactly. Exactly. That is the key point. You see, the L by D ratios for steel are going to be higher than the FRP. That's because of deflection. I want to keep emphasizing. I didn't go into the deflection part of it. I will show you that a little bit because those are on the subsequent slides in my theory. But what I want to say is, I told you many times already, the deflection controls, but the important message is that deflection we are talking about, like say PL cube over 4080, that I value is the effective, I effective, not I cracking, not I gross. That is the message I want to convey. Yeah, and that is the reason why we have a higher L over D type for steel.
Just adding on this.
Sure, please do, please.
That addition of discrete fibers, I said, either synthetic or steel, greatly helps in improving your flexural rigidity.
Right.
Then you can cut down the rebar, then the design becomes more economical.
Exactly. That plus, from a fatigue point of view, it's a great help. That is why I never understood why it did not take off. I don't know why. I mean, if I were doing it, I nearly need to tease Suru Shah. What the hell, you got 20 years of funding, what happened? I don't know. I'm serious when I say I don't know what the reason, but it has a lot of advantages. So, but anyway, so you see right away how inaccurate potentially the approximation is. What did we do? I said L over 17 or 16, I got 13.4. I'm trying out 12-inch thickness. May work, may not work, that we will know in my next step. But that's what we did. So here is this slab, self-weight, and there is no superimposed dead load. Now I'm going to answer, okay, here. Here I said 11 and 17, if you remember. So it depends on the two-way slab or a one-way slab. In this case, they are taking 14 and 10. Again, that is up to your code. Our code clearly defines this. That's my point.
So
okay.
We also have a code coefficient that gives you on a table what should be the value that it should be.
Yeah, we have that same thing. The code I gave you, American 44011, defines those numbers. Now, I'm trying to add Dr. Chan's question here. Please look at this. 1.2 times the dead load, 1.6 times the live load, and that is the live load moment. This is the MU that must be lower than the phi times MN. That is the design approach. If this MU is not lower than the MN times phi, I keep calling phi MN, then the design did not work. But if phi MN is higher than this, it worked. So this is where, this is only one check. This is only one check on that table we just showed you. There are 6 other checks here to make only in the strength aspect. Likewise, you have 3 other checks in the serviceability aspect. There are a couple of other checks for extreme events and for fracture and fatigue. So this is an involved process. If you don't have fracture fatigue issue, you don't have to check for it. But you must check for both strength and serviceability. I know some of you know some of this. I'm also trying to convey a message, especially to the manufacturers, So they need to be aware of this, and they should be equally aware in promoting the FRP by suggesting some of the ideas like this fiber concrete, which would help a lot. Those are the kinds of. If you have any discussion, please let me know. We would discuss it. So what's our goal? Our goal is to find the magnitude of FRP, assuming this is a tension control. So here is the clear cover. So what does that mean? FFU, let me go back. You see, FFU star is 90,000. FFU is the factor 0.8 or 0.85, the CE factor. In this case, we use 0.8, but you can use 0.85. Different codes are using different facts. But the message is FFU is the one our design controlling factor for the design. See, right away, I like to emphasize the average value, the average value of this is what? About 25% higher. Like you're talking about 110 in that range. And we reduced it -3 sigma. And that is what this number is. So keep it in mind, your average is not what it is. So my message is, I have 110 KSI FRP, while in fact, I am using 72 KSI as my design value. So right away, you almost have a 50% reduction. You see, that's only one factor. We have load factor, therefore we have a 1.6 or whatever that. You see? So when you add up all these factors of safety, it comes to 5, 6, 7, 8, in that's what happens. It's what happens,
Sir, you told to check the different load combination cases. Even if the bar is being used in zone 2 sections, there too we will have to check the seismic load combination? No,
the load combinations are static values. The earthquake type things you are talking about are the dynamics. Only for the earthquake part, this you have to check. There's no way out. That has to be checked. But the way you go about checking for level 1, 2, 3, 4, 5, 6 is different. That is either a pseudo-static or equivalent static or a first mode, first fundamental frequency based. The analysis gets complicated from 1 to 2 to, whatever that is. Right. But what they are saying is, maybe this is your question, for low levels of earthquake, which is say category 1,
yes,
we are permitting you to check in whichever the way you want to check with FRP. But you go to category 2 or 3 or 4, we are not guaranteeing how FRP works. Therefore, code is not giving you any direction of how to design for level 2, 3, 4,
yes,
5, 6. That is the clarity. Okay. So if you assume a tension control, you don't have to. That's entirely up to you as a designer. Then there's a clear cover, and F sub FU we already determined. So if my D value is 12 inches is the total depth, and you subtract the clear cover as well as half of the diameter of the rebar. So that gives you cover, not clear cover, That one in the parentheses, 0.75 plus 0.625 over 2, that is called cover. 0.75 is the clear cover. Sometimes the terminology is also, not simple. Okay. So again, from the strain compatibility, you know that equation coming straight from that one on that green board. The C value is 2.2 inches, and M being a tension control, that's what we are talking about. Again, the phi factor, please note here, mu is phi times mn. Exactly. So phi, if it is tension control, 0.55, then this is the amount of area required. I know my m sub u because the previous thing from a design, at least for one check of those 5 or 6, that's what m sub u I know, and that is a tension control thing I know. Therefore, I am substituting all those. B1 is what is B1? If it's a 4,000 psi count, beta 1 is 0.85. If it's a 6,000 psi, beta 1 is 0.75.
Yes.
Like that. So FU, we already talked about it, 72 KSI. That is FU. So anyway, from there, that is what we got. What we need is 0.26 inch square per foot width of your slab is the amount of reinforcement needed. Okay. Again, we checked for rho F min. This is very, very important all the time. This is the rho F, AF over BD. There is a limit. This has to be bounded between 0014 and 0036. There are reasons for that. That's a code requirement, not mine. And you can see. So what we need as a minimum is 0.52 inch square compared to what we got based on the load. Therefore, this is what controls. And number 5 bar is what, 0.3 square inches or something like that? 7 inches. So 0.52, I mean 0.3 divided by 0.52 times 12, that is a selection, comes out to be roughly 7 inch centers. You see how, I suppose, the reason I'm explaining, I don't need to explain for a structural engineer. For non-structural engineers, I need to explain how we got from here to here, okay? Corresponding to this. So it is the area of number 5 is 0.3. That divided by 0.5, where are we? Yeah, 5.2 times 12. Okay. All right. So do you see how we arrived at it? For a one-way slab, a two-way slab is much more in tension. A two-way slab is much more difficult. So now what we are asking is verify these assumptions. So we have placed 0.53 amount, if you look at it at the back, we have, instead of this gives you 0.53, even though we only need 0.52. So that is what we are trying to, so we are making a check. So first we want to make sure it is tension controlled or not. That's what we did based on the balanced approach, which we talked first thing in the morning today. So these are some of the notes. For positive moment, we concluded we need 6 foot kips per foot. Then the minimum GFRP, number 5 bar at 7 inch. Slab design must be checked for shear, crack control, creep rupture limit, and deflection. So I haven't done that yet. I will do that as a, next step or later. not an efficient design, because the slab thickness can be lowered to satisfy crack at this service load. Remember, what did I say? You dabble, if it is not an efficient design, you can reduce or increase, in this case increase, the amount of GFRP. Then reduce the slab thickness, so you have a less self-weight. That is how you need to think as a designer.
Why we are not adopting the compression control in this case?
No, this is just an example. That's all. I'm trying to illustrate a point. No, definitely if I were a designer, actual structure, I'll be using a compression control. Yeah. But here, remember, we have to check for two things, right? Bending moment on the tension side and the compression side. The tension side is between the beams, the compression side of the moment, which is WL square over 10, over the beams. Okay. So redesign for cracked slabs at service. So GFRP slab for flexural service strength is, so that is per the code, 0.2. That's the key point. All the others is mechanics, you can do it, but that is the key issue. The thumb rule is designed for flexural strength, that is twice the ultimate moment, and typically, like I said, we assume for compression control 1.5 to 2%. No, don't exceed more, I'm sorry, I didn't say it right. 1.5 to 2 factor of row balanced, So don't exceed more than that, 1.5 is a good number times the balanced value. So we already found the balanced value in the earlier slide, 0.008, and we are saying for a compression control it is 0.12. From there, again, as soon as you talk of compression control, you have to use that quadratic equation. And my feeling is, I haven't thought through enough, but I can bet you, this can be, first of all, I said we can throw this term out. That's first, But second of all, I really believe even this can be reduced and removed from the root and use a lump sum factor that will give you an answer. That's neither here nor there. I'm just saying how one needs to think through as a designer, not as a mathematician. So for compression control, you see, we are talking about, we still have a lot of reserve. If it's a compression control, our strain, the stress is only 57.5 KSI. It could be 72, you remember that? Yes. So we still have 25% waste. But that's okay. That's where you need to balance this out, as much, push it as much as you can by, you remember I told you a few minutes ago, by reducing the depth of the concrete or whatever. Of course, you can only do it so much. Okay, here. So we're selecting 8-inch thick slab as opposed to 12-inch thick slab when we did the tension control. That is the point, isn't it? So now suddenly we reduced a good bit amount of, you keep asking me about earthquake design. The first thing people worry in earthquake design, how much can I reduce the top heaviness of any structure? The dead load, we want to minimize that. So this is an excellent example.
In fact, in a building, the majority of the dead load comes from slab.
That's right.
Optimize the thickness, you reduce the demand.
And that I'll extend that statement. As the building goes up, like say 10 stories, 20 stories, 40 stories, say, it is essentially the dead load that controls the design, not the live load.
Yes.
In bridges, let me tell you, if I have a 100-foot span bridge, my dead load effects are say 25-30%, say call it 30. the live load effect will be 70%. I extend that argument from 100-foot span bridge to 6,000-foot span bridge. The dead load is 90% and the live load effects are only 10%. The same argument goes, especially so for earthquake type systems. So as a designer, you need to keep some of these in mind so you can, see here is a great example. We reduced it from 12 to 8 inches. Very simple, very rudimentary. You can't get an example simpler than this. You know, as a designer, there were many other complexities. I didn't even introduce any of them. But for the simplest possible, you can see. Now we are going to talk about your negative moment QL square or WL square over 10, positive moment WL square over 17 or 14 in this case. So L, the effective span length is 18 feet, and the M sub U has the phi factor, and here is another simplification of all that. So what did we find? All you need is an effective depth of 5.7 inches. So if somebody is very critical, they can reduce it to from 8 inches to even 7 inches and still get away with 5.7 inch effective depth, total depth of 7 inches. So that is how, it is not just the savings in the materials, which is minimal, it is the overall efficiency of the design. The self-weight. Yeah. So, modified factor for 7-inch thick slab. So we went back and reiterated that. So we did a similar kind of a thing, went through the, but now I want to talk a little bit about temperature and shrinkage reinforcement. I don't know what your code says. Our code is saying it should be the rho factor for shrinkage and temperature is 0.0014 as a minimum times BD. You know, the effective times.
Here it is 0012 for steel.
Okay.
But we don't have a code for FRP, probably slightly higher.
Yeah.
In GFRP.
Yeah.
In RCC it is written as 0.001.
In my opinion, assuming 0012 or 1 is okay, it should be lower than that because the coefficient of expansion is much lower in FRP than in steel. Okay?
So actually, most of this shrinkage problem what we are finding is, yes, as in temperature effects are less. Mostly, you know, at least in Indian context, you know, they use higher water cement ratio.
No.
That tends to be the major.
The shrinkage issue.
Yeah, shrinkage.
That's right.
More fibers.
That, you see, I don't know you were here when I was saying. When we were pouring concrete with reference to the McKinleyville Bridge, our regs are very, very stringent. So the guy, the ready mix guy did not meet the standard. He had to dump some 20-30 cubic yards of concrete. Now, talking about your statement, we do not allow more than 0.35 as the water cement ratio. Maybe even a little bit less. That is correlated to the slump. We do not allow vibration more than, say, 20 seconds, actually 16 to 20. If it goes more than that, you know what happens? There's a separation or segregation of fines from the coarse. Okay. We want the vibration to be spaced at 20 inches. We even have a definition of RPM. So when I say 16 seconds, of what RPM am I talking about? So it's all related. So we are that stringent about it. And I've seen concretes here, they easily have, on an average, I dare say, 0.55 to 0.6 here. 0.5 to 0.6 is the water cement ratio in India. At least the ones I saw. It should be.
But now it has come down.
Come down. Okay,
with
good.
all the advent of super plasticizers.
Uh-huh.
But at least in the contractors who are big contractors, they don't go anything more than 0.4.
Okay.
And
Good.
But at the lower level, the small residential construction, it's being still done by people.
Workability is the dominant factor there.
Yeah, that's the major. That's where they tend to add water. The super plastics are costly. The strength is not really a big governing factor in residential construction. Concrete strength.
We are using super plasticizer rather heavily and effectively in terms of geopolymer concretes. You see, we don't use any water. In geopolymer concrete, zero water. 70% of fly ash. And the only way you get the workability is by using the super plasticizer. See, have you done a geopolymer concrete in the country today? No.
This is we have a lot of work, I think.
No, I mean in the construction, I meant. I know, it's in the...
Precast plants they're doing.
They are? Oh, good.
Yeah, but not really the full-fledged, we cannot deliver, order a concrete from RMC will deliver a geopolymer.
So what type of curing you are adopting for geopolymer?
We are not adopting any curing other than your ambient, that's it. We built what? 150,000 square feet plant to prefab the modules. 125 or 150, I forget, but it's in that range. Yeah, we are not doing anything other than, and we are attaining about 80% of the strength within a day. Roughly 75, 80% within one day, I mean. Yeah. I think the super plasticizers help, and the proportion of some of the other admixtures are helping us too. So it is quite a bit dependent on two things: the local quality of fly ash. Oh, that's a killer. That's a killer. And the second one is, remember, don't ever use geopolymer concrete without certain amount of aggregate. You may get the strength, but creep is a killer. If you do not have adequate amount of concrete, it can creep like crazy. Yeah, so it can. We never got, without coarse aggregate of certain range, we normally don't go beyond ½ inch for geopolymer concrete. We even proportion the coarse aggregate. That's another stringent requirement for us. Like 3/4 or ½ inch, but here geopolymer we only go max ½ inch. Without it, believe it or not, we didn't get a modulus more than 1 MSI, like 6, 7 GPa. So much so, what it did is creep load primarily under the self weight has resulted in slow but steady increase in crack growth. By the time we realized it, it's too late. It looks good on the first day or 2 days. Once you go beyond that, you'll begin to see the cracking. So that's why I asked you, are you people getting into high-level construction? Not in the labs. I know actually a very good bit amount of work was done here in these countries, like Singapore did a lot of excellent work from you all. There's somebody here from Karnataka, I forget his name. I followed some of his papers. They did some good work.
Our colleague Professor Subramaniam has done a lot of work. But mostly, as you said correctly, now they're looking at blocks and small elements which can be done with precast. And handling that alkalis, that is an issue still that need to be resolved.
Right. So that's where we are on that. So sorry for digression, but at any rate, that is the spacing we got based on. You even modified it from 8 inches to 7 inches, you see. So you can see how we take advantage of. Now, this is the most important thing when it comes to GFRP. What is most important? Crack. Why is it so important? Because of low modulus of FRP. So again, these are empirical values given to you there in terms of this check when I said empirical value. So keep that in mind. So here CE is 0.8 or 0.85. I will leave that to you depending on your code. And this is a beam, and this MU is inclusive of your load factors. So we need, whatever we're going to do now, we should make sure that the MU or M phi times Mn is higher than Mu. That's the idea behind it. So here, the most important thing to keep in mind is the service load moment, not the ultimate load moment. Means what? We don't have to worry about the MU part of it, like 1.4 dead load or 1.2, 1.6, those kinds of things. That's why that tabular form is very important. Keep that in mind. Whatever the crack width controls we are talking about, do not account for load factors like we do in terms of MU. Okay, so you can go through that. The max crack width they're suggesting is 0.028. For our bridge decks, the crack width is around 1/3 of that for our bridge decks. That's steel based, but we can relax that. When you talk of stringent quality control related issues, the reason we have such small crack width limit state because the de-icing chemicals go through and lead to corrosion, and that's what we're trying to minimize. And also we increase the cover from 1 inch to 1.5. Today our cover on the top is 2.5 inches. That's for bridges, not for buildings. Okay, so we can go through that. We select the 4 of number 7 bars. We're going to make some of these checks in terms of the crack width, and the equations I told you are given right there, section 7.31, and this is the equation. So you can see, once again, we are talking about the elastic analysis. We are talking about service load. Means what? We are only looking at I effective, not I cracking. So again, the D value, the effective value for this beam is given to you there, and the modulus. We have 2 equations to establish the modulus of a concrete based on F prime C. This is an easier equation. F prime C times 57, slightly inaccurate than the other equation. I gave you that other equation if you recall, but this is a little bit easier to compute, and the elastic crack analysis where we found the K value. I'll show you that in a minute. NF is the modular ratio. That is the stiffness of FRP over stiffness of concrete.
Generally, the cracks occur at the contact area of concrete and bar.
No, not at all. It should not. Then you lost the game. It is, like I said many times, crack, no matter what you do, concrete cracks. Due to shrinkage, for example. Yeah, exactly. It's a tension crack, so you are talking about 300 psi, 400 psi to tension failure. Naturally, concrete would crack.
Under service codes also, we allow cracking, but we limit it.
That's right. So
what is the minimum limit for the crack?
That's what I gave you. 0.028. There we go.
Maximum crack.
That
Yeah.
multiply by inches, how much it's cracked, and
Yeah.
The crack at half millimeter propagate to the
half a millimeter also. Because here it is higher. It's not going to curve right. So the maximum allowable crack width, 0.028.
That is what we gave. And that is, FRPs can tolerate a little bit more cracking, crack width, I mean, because of non-corrosiveness. Like I told you a minute ago, for bridge deck, that number is 0.01, 1/3. So that is a typical number. Talking about a minimum crack, we love to see 0 crack, right? That's as minimum as you can get. So the K value, you can see under service loads, you have a K value of 0.14 times D. KD is, say if it is 20-inch D beam, about 3 inches is the uncracked part. Typically, if you remember yesterday we talked about, they are using 0.16. In this case, we got 0.14, but they're normally using, that's for service load. For failure load, it's about 8%. And an average number is the I effective, means the I value cracked section under service load is about 1/4, 1/5 of I gross value, and the I crack value is about 1/10, 1/12 of. These are broad numbers again for the designers. That's a good guide, So that is why we keep emphasizing the service level stress. That's the key. So if you look at the I cracked value, I don't recall the IG value. This is typically about 1/10 or 1/12 of your I gross value. I don't know that I have that here or not, readily available or not, but that's about what it is, So you can kind of figure it out, 112 BD cube. So that will give you whatever the number you're looking for. So this is the stress of the cracked section. For elastic cracked sectional analysis, we found the K and KD values. K is 0.14 and KD is 0.14 times 21.56. So that is approximately 3 inches. That's the limit check. I already gave you that equation. I really do not know where they got that equation from, I admit, but that's the equation. And the bond coefficient based on the depth is 1.4. Again, that is a empirical number. So what we figured out is from all this that this check did not satisfy the limit state. Therefore, we're going to continue to check the bar spacing for different purposes. The S max equation, again, that's an empirical equation, and that satisfied it. So these are the empirical checks. From the code, I identified the equations for the empirical checks. Okay. So that is the bar spacing. So that concludes essentially the crack checks. Okay.
The best, as you said, reduce the bar diameter and increase. That's the spacing will become less.
So we'll go to the other example next. You want to break?
Take a break.
Sure.
Coffee.
Sure.
So we can take about 10 minutes.
Absolutely.
Also have a class at this.
Sure. So we'll take a 10-minute break and assemble back at roughly 11:45. Control cracks, you need to reduce the reduce the spacing. That's how.
Bar diameter reduce the spacing.
So, I mean, that's where you control the crack. That is why in this equation, you always see the diameter is tied to the D value. Somewhere it is there, you know. The diameter is tied to the D value. Yeah, anyway.
Will it happen always? Like if
You have to check.
reduce the crack,
Happens or not, you have to check for it.
what is the general trend? Sir?
It doesn't really happen. Generally, it is the deflection that controls, not the crack width. But they want to make sure you satisfy all the requirements. So you work for a company?
Yeah. So I recently graduated from Queen's University.
Canada.
Yeah. And I moved back to India in January. So currently working as a structural designer.
Uh-huh. There used to be a guy at Queen's from, that's at Montreal, right?
No, Kingston. It's nearby. It's in between Toronto and Ottawa.
Oh, okay. Yeah. I used to know some people there at Queen's, yeah. Okay, very good, very good. How are the employment situation there?
In Canada right now, it's really bad.
Really bad?
Yep.
Coffee, sir?
Coffee.
Your coffee? Too.
No, I'm fine. No, I'm okay. I can.
For beam, suppose for beam, for column, for slabs. So for all the things, you have to check all these parameters like
Yes.
compression,
No. You don't have to check. You have to determine up front. Am I going to have a tension failure? So, we are going to look at deflection now. I already told you the three deflections: gross deflection, crack deflection, effective deflection, depending upon your I values, I crack, I effective. Let's look at some of the deflection related issues. Here we are talking about a beam 12 inch by 24 inch depth with a 2-inch cover, 4 of number 8 bars, that's about 0.79 inch square, and the span is about 25 feet. Consider long-term deflection at 3 months and 5 months. What is that?
5 years.
5 years. But what is that? That is the creep deflection. That's the key.
Long term.
Long term. Typically, after 5 years, they say creep deflection is pretty much constant. It does not increase. So it is an inverse curve, goes up. About 60% of total creep deflection takes place within about 6 years. 80% takes place within 1 year. About. After, of course, there is going to be creep after 5 years, but maybe 1 or 2%, but it's negligible. That is the word. You will see some of that actually in the code. I don't know, that is the subsequent slides that I did not show is where I have the creep deflections as suggested by the code. I'm not sure I can quickly find those values or not. Yes, I did. Okay, we will look at that. I'll reiterate that. That is slide number 152. Okay, now mine. Okay, yeah, 152. If you look at it, time-dependent values for deflection. So what you're going to do is find you can see the coefficient is equal to 1 for 3 months, 1.2 for 6 months, 2.0 for 60 months. So they are saying, as you were asking me a minute ago, they are saying that after 5 years, it is pretty much same. So that's what we are going to try to find. This is the psi value is what's going to be modified, So I'll go over that later, but please look at it. So you have 3 stages. This is the instantaneous deflection due to the loading. And if the load remains constant, of course the load is a sustained load, not a live load coming in and getting out, a sustained load, then if it is a sustained load, it's going to go up. When you remove the load, the recovery will never ever be back to 0. When you remove the load, yes, there is some recovery, but that is less than the creep deflection, which is from here to there. So these are some of the issues, keep in mind. So let me repeat myself. Immediate strain means what? Elastic deformation, MC over I, where M is due to dead load, let's say, not due to live load. So that creep rate, creep deflection magnitude, they vary depending upon the percentage of the dead load in relation to its failure load. So higher the dead load, higher the rate of creep, of course higher the magnitude, we know that, but it also increases at a faster rate. So there are the two parameters there. One is the magnitude of the sustained load, and this is a function also of the time factor. I don't know how many of you are aware modulus E value is a time dependent function. So if I have applied the load suddenly, I have a modulus higher than the static one. If I applied load gradually, I have a modulus that is lower than that. There is something in between. Therefore, how we are going to come up with a generalized theory that would account for the time-dependent modulus, that is a very fascinating topic. We have ideas, but we never came up with a unified theory for these different load rates. That's what we are working on, actually.
In precise concrete also they will consider the creep coefficient when they are when they are considering the Young's modulus.
Right, which is, we call it as a very low load. If a bullet hits, that is a high speed. So there the modulus is higher. In creep, the modulus is lower than the static modulus. So you are always comparing higher or lower with the static value. Okay, that gives you an idea. Now we can go back to, yes, sir.
Recovery, what are we talking?
If you remove the load for whatever reason, some of the creep deflection will recover, but not all of it. Is that your question?
Is it same for both, like if you are taking like a slab or like in beam type, wherever the horizontal GFRP comes into picture, and when you see like columns, both will be like same or it will be same?
That's what I just said, meaning depending upon the induced stress level, the rate of creep changes. Okay, let me quantify that. For example, my failure stress is 100 units, say. If I put 10 units of sustained stress, it's going to have creep. If I put 25 units, it still will have creep. But at a 10 unit level, the rate of creep is slower and it will reach certain value, whereas at 25 per unit level, the rate of creep is higher. It will go to a different kind of a value. That's what I'm saying. But after 5 years, it is leveled off. Creep tests are done for 15, 20 years, really. You have to keep monitoring, see what happens, how it does for different stress level conditions. So for a percentage of bending stress, for example. So with that, we'll go back to problem number 5. Slide number 200 something. 220. One more. There we go. Missed it. 214. Yeah, there. So now did you get it? Deflection corresponding to the creep issue. That's what we're going to be discussing. So along those lines, I did not talk about the deflection limit state. We have, these are the deflection limit states. There are 4 different values that depends upon which one do you use, the code, and where you use, the code clearly identifies. So, from my recollection, L over 180 is the deflection limit state for cases of the roofs that do not have major failure concerns. The lower value, one L over 480, roofs with a major concern. Okay, deflection limit state in the US, we primarily state it's a function of human response, meaning as you keep walking, for example, then the floors vibrate. You don't want that. You feel odd when that happens. You know, that is a human response problem. In the olden days, most of you don't know, we still use wooden floors. You all don't use any wooden floors. If you go to villages, you still find wooden floors. They have a fairly high vibrational issue. That's why we have a deflection limit. Actually, that is a misnomer. Talking about the deflection as a function of span is a kind of a misnomer. It should be really related to the curvature. What is that? That's essentially the slope equation. L over delta is what we are saying is 180 or 480. 480? Yeah. See, that's L over delta. What is L over delta? It's a slope issue. That is not right, because I can have a tremendous curvature and have a failure, but still meet the L over delta as 480. You see what I say? Never mind, I don't want to get there. But another application where deflection limit state becomes critical is in the hospitals, where you have these MRIs, when if it is vibrates too much, gets off focus. So you want to have that. So primarily it's a human response issue or a sensitivity issue for medical instrument. That's where we have. So again, we will go through the same. So here, the important message I want to provide you with is the deflection limit based on creep, based on sustained load. The code is saying this is the key, that is the key step. Unlike your ultimate load combination that I gave you earlier for strength limit state, now I'm talking about this serviceability limit state. Here, you cannot avoid dead load. That's always going to be there. What they are saying is, to find the deflection, you are going to use 20% of the moment corresponding to the live load. That is the message I want to give you from this slide. Okay, so here you have the dead load there. WL square over 8 is a very simple case, and you have a live load there, and then the 20% of the live load moment is what we are talking about as a sustained value. So they are accounting for, if you remember that slide 155 or whatever I showed you, he was asking me a question about the recovery. So we are saying there is a residual deformation. There is a residual deformation coming from the live loads. In other words, there is no, just because the live load is gone, there is no full recovery. In concrete, as you know, they tend to use, I'm sure most of you know, if not all of you know, use what? Modulus as 1/3 of the regular modulus to account for creep. You remember that? In that range. Some people use 40%, some people use 33%, right? 1/3, roughly. That is the creep deflection. So you are going to compute total deflection, including the creep, by reducing the modulus to 1/3. That's a good bit. I mean, that's an easy way to do it. That component gets very difficult computationally when you deal with pre-stressed concrete beam design. I mean, that is an approximate number, but if you deal with a pre-stressed concrete design due to the pre-tensioned loads and what have you, you have to make a combination of live load, dead load, and the pre-stress loads. That is where they use the factor. That's what we use. I don't know what you use in India. 1/3 is our number for creep. Maybe while the
For pre-stressed too.
Huh?
For pre-stressed material elements too, it's 1/3.
No, we use 1/3 as the, I mean, if the modulus of concrete is 4.5 million, for static loads, for creep load, we say, no, it's only 1/3 of that, which is 1.5 million PSI.
Sir, the deflection, the significance of checking the deflection in 3 months and 5 years is that before 3 months it is just due to the sudden loading, not the creep comes into play.
Oh no, it does come. Remember, okay, let me state it in the following manner. I just said 98% of creep deflection takes place in 5 years. But I also said about 60, 70, 80% in the first year. In 3 months, approximately 40 to 50% of creep takes place. You follow me?
That's why 3 months is a significant.
You can see that from the equation there that the creep coefficient, that numbers 1, 1.2, 1.6 and 2.
Creep recovery.
So, no. Okay.
The value of epsilon.
That is, let me go back. Is it working now? See? Oops. Yeah, there. So if you see it, it is the creep deflection is about 0.6 or 60%. Yeah. Then it becomes twice that much in 60 months, and the rate of creep is not linear with respect to time. It is not. That is why we showed you the plot. This is the instantaneous due to dead load or whatever, but whereas after it hits the dead load, there is a gradual recovery. In this recovery process, gradual increase, I'm sorry. In the increase process, what we are saying is, whatever the live load effect you have, we are only considering 20% of that over and above the dead load creep.
So it is said that until the load acts on the structure, creep doesn't start.
Creep doesn't start till you remove the shoring component. It only starts after you remove the support condition, the shored conditions.
In the initial portion, it is acting because of dead load.
Even that is zero. But initially, once you remove the shoring, that immediate is primarily due to dead load, but you could have some live load as well, meaning it doesn't have to be human beings as the live load. There may be other kinds of live loads, like people walking on it, What we are saying is that live load for computational purposes is only 20% from creep deflection computation point of view. Okay, so we go back to page 215. So the message in this, all the others are same, WL square over 8 or whatever, all that is same. But what is not same is computation for moment corresponding to the sustained load. That is the difference. And this is the modular ratio. Then we move on. So here, I already told you the gross moment of inertia is 13,000, and look at the cracked moment of inertia is 2,200. That's where I said it's about, in this case it is 6.5 times, it could be of the order of about 10 times for a cracked moment of inertia. And then you see how we found the cracked moment of inertia? 1/3 BD cube, but that D is the effective depth, that's why it is KD cube. K is the factor that defines the solid portion of the section, and that's where you get the neutral axis. Then you have added on, what is this? AD square effect. What is the AD square effect of what? Of FRP. You see how they compute the number? And that turns out to be 2,200 compared to the gross value. That's about 6 to 7 times, Oh, yeah, it's right, given right there, 6.24. Now let's look at the cracked. Where is the M cracking coming from? That is, MC over I is equal to FC. What is that? 7.5 times square root of F prime C. That's the 10th rupture value, we call it. And from that rupture value, 7.5, you see all that, you can MC over I type stuff. 7.5 times square root of F prime C. And lambda is a multiplier for creep. We already told you. Lambda is 1.2 or 2.0, depending on the number of years of creep you are accounting for. So that is M cracking is F times I divided by C. That's exactly what that is. F, that is 7.5 times F prime C is the I divided by C. And lambda is the factor corresponding to, in this particular case, we're taking lambda is 1. But now the question is, that is IG is all right, that's a general term, but now we have to worry about, is it IE or I cracking or IG, that is the question. So, as you can see, M cracking is 39.5, M dead load, live load without any factors, and that number is 0.7. And this is the empirical equation given by the code to establish the I sub effective value. This is the empirical relation. Therefore, I need this ratio to establish what that gamma factor is as per the code equation chapter 24. So I effective, you remember what I told you? I don't know you remember or not. This is approximately twice the cracking value, if you recall. So that's what we are talking about. So it is this IE is what we are going to use to establish deflection under service loads. So what is the difference between deflection under service load and deflection at failure? If I have, let's look at it from the standpoint of the physics. If I have a beam under bending, meaning some applied load, there is going to be a crack like this under service load. But on the other hand, if I'm going to take it to failure, that crack is going to go up to there, and then ultimately it will fail in local crushing of concrete. Now, we are not talking about totally cracked system, no. For service purposes, we are talking about I effective, meaning it cracked all right, as we discussed this morning before the break. How much did it crack? How much do you think it is cracking? And that is what is established empirically based on lab type testing and what have you. This equation, this is the critical equation, and that is tied with M crack is the section property, M sub A is the applied load based property. And when you talk about M sub A, that does not include your load factors. Ultimate values are different. You need to have a clarity in terms of the design. Ultimate strength design values are different from serviceability based design values. So, as I indicated to you, this is approximately twice that of I cracking. Now you understand the difference between a cracked section versus effective section? Okay. So this is why we say in steel reinforced beams, is a tension failure in steel, but it's a primary tension failure, secondary failure you have. Ultimately, it fails in local crushing. But we don't want things to go that far out of control. Okay, so now you can see immediate delta with k is equal to 1. That's a length factor. And the delta using I sub E, that equation, empirical equation I showed you in the previous, is a very conservative number equation. And you can see the I sub E and then delta corresponding to dead load, live load, delta corresponding to live load only, and the difference is 0.37, and the delta corresponding to sustained load 0.305. So the delta from the unsustained load is 0.457 minus 0.305. So that is the delta from the unsustained load without multiplying with a creep coefficient. Now you have to multiply with a creep coefficient to establish the total deflection, including the creep, for the sustained load condition. There we go. Incremental part of delta, after placing non-structural elements, some of the long-term delta from all sustained loads and the immediate delta from additional live loads. Now for 3 months, you can see we have already computed these numbers in the, in the previous slide. These numbers in the previous slide, you remember 305 and all? The sustained load numbers after 5 years, you can see how much the deflection has increased due to creep. Almost 50%. Little more than 50, but in that range. So the creep has a tremendous impact on limit states corresponding to the deflections. So that is my message. Compare the computed delta to deflection limit states. So these limit states that I'm showing you here, L over 180, L over 360, it is given under what condition they're applied. The definition is given right there. For flat roofs without non-structural elements, it is L over 180. For flat roofs without non-structural element likely to be damaged by large delta. Okay, so now you have to worry about the allowable values that are for different kind of scenarios. There are 2 others. You remember I gave you 4 of them: L over 180, L over 360, L over 240, and for L over 240, floor supporting non-structural element not likely to be damaged, floor supporting non-structural element likely to be damaged. So these are defined by the code. We have nothing to do with it. So you have to satisfy all these items. If they don't satisfy, obviously what do? You go back and increase the size of the section, or increase the amount of reinforcement, or the quality of your material, like concrete strength, you know, one of those variables. Huh? Okay. One is flat, you're talking about this, flat roof without, and the one is with. Sorry. No. There is an editorial error. Did I answer your question? No. I couldn't hear.
So which one is without non-structural elements and which one is with?
Okay, I'll throw the question at you. What is the common sense telling us? Okay. The first one is not likely to happen. Wherever you have less risk of failure, the limit state is lower. Wherever you have a higher risk of failure, the limit state is higher. That's what it is. Okay. So you can see the factor is going up by 50%. I don't know how many of you all design the floor systems for deflection limit states here in the country? You do? Yeah. We not only do this, we also have another limit state in terms of frequency. Now, the first fundamental frequency should be below 3 hertz, for example. That is tied to the human response. 2 to 3 hertz is tied. So, either it should be below 3 hertz or above 6 hertz. Between 3 and 6 hertz, things come close to resonance. They don't resonate, they come close to it. Okay. So, we talked about limit state from the standpoint of deflection.
Yes.
Now we need to look at the same kind of a limit state from the standpoint of creep rupture stress check. So it's a rectangular beam, 12 inch by 18 with 3 inch cover, 4 number 8 bars, carries the load. These are just some numbers really illustrating the point of the principle more than anything else. And assume that 20% of live load is the sustained value. So again, the drill is same. Concrete modulus, we said that 100 times. The rho values, we know how to determine. Area divided by the cross-sectional B times D. D is the effective value. 3 inches is the cover. So again, we want to talk about sustained moment. There's the dead load is always 100% sustained. 20% is the live load sustained.
Sir, if nothing is given in the statement, then we have to assume only 20% of the live load is being sustained.
Correct. That is by default. You may have a much higher sustained load due to utilities, for example. You see? So that you have to check it. If nothing is given, you assume 20%. So we find the eye cracking as we did before. The first term is a 1/3 B kd cube. The second is the AD square effect. Eye cracked value is 861. So the allowable stress is 6.55 less than 0.2 FFY. 14.4, therefore that check is good. So creep rupture, find U stirrup size and spacing for 20-foot span simply supported beam. Here the B and D values with a 3-inch cover, 12 inch by 24 inch, the D effective is 21 inches.
We are changing the power from DC to mid-side.
Oh, that's fine. So while we are at it, all I want to say is we talked about the bending cracks going from bottom up, and at some point the concrete will crush, and the effective depth of the neutral axis for steel is about 15, 16, 17%. For FRP is about 8%. Whereas the shear crack, I don't think this will work, the shear crack is going to be something like that. And this is where I want to repeat myself. The L over D value. So L over D value is say around 20, 24, definitely less than 36, 38. This is bending failure. Whereas for a shear failure, L over D is less than or equal to 12, less than or equal to 6. So this is the shear failure. Okay. So now we are going to another example where we will have a creep rupture stress check. Find the U stirrup size and spacing for 20-foot span simply supported beam. So we gave you the loads and the member size. Why did I say L over D should be less than 12? It's a shear failure.
Yes, sir.
That's the reason I reminded you. And the CE value can be 0.8 or 0.85 depending on the code. And that support, 20-foot span, is, I don't know how much you all do here in terms of shear critical section. Do you all use it at the support, or do you use the critical section at a distance D from the support? Yeah, I want to repeat this. Typically, the critical shear section is at a distance D effective depth from the support. Only, wait a minute, that's partially correct, partially incorrect statement. That is, if you have any concentrated loads, any other special loads, or the loads are placed at the bottom of the beam as opposed to the top of the beam, then you should not take the critical section should be at the support, not at a distance D from the support. Do you get it?
In Indian code, they'll say that when your support reaction creates the compression on the
Correct.
beam, then that is at a distance of D from the face of the support.
That's right.
If your support reaction creates the tension, then it is at the face of the support.
Yeah, that is what I mean. If I have a beam, what did we say just now? Critical section is not here. We are saying critical section is there, right? But that is at a distance D, where D is the effective value, correct? But what we are saying is, that's correct partially. If on the other hand, if my load is not here, if the load is say here, for example, I'm just using that as an example, then you have to take the value 0. That is, okay, all right. That said, let's move on. So, that's, oops. So that's what we are talking about. Okay, 5 kips per foot. So the V at a distance D, we have proportionately reduced that effect. That square root should come right here. It did not. It's a typographical error. Phi factor is, as you know, even today we don't fully understand how the shear functions on a cross section. Therefore, you always have a higher, uncertainty, therefore lower phi factor. And this equation is given by the code. The K value is established based on that equation. I'm glad we talked about it first thing in the morning today. The phi factor is 0.75. Correct. So the square root value is properly placed here, unlike on the previous one. So the phi V sub C is so much. I don't know whether it's the same thing requirement in the ACI code for in India or not, but we say you don't need any stirrups if the V is less than that. In other words, in this case, you do need stirrups, but we say you do not need any stirrups if it is less than that. So, that V is missing here, VU minus VC. So if you have the value of shear higher than this, we have to modify the section. In this case, it is not, meaning 8 times square root of F prime C is our limit. And that's the upper bound. If it is the case, we have to modify. And the lower bound, it is 2 times square root of F prime C. We already checked that. That's what that is, 2 times square root of F prime C. So here we satisfied the upper bound in terms of stating that stirrups will do the job. That's what it means. If it exceeds that number, then the stirrups will not do the job. You have to increase the cross section or increase the property of the material. That's what it means. Again, we are assuming that the critical section is at certain distance at the support, and that is the ultimate load. Therefore, we have established the distance from the support beyond which the shear the reinforcement is needed. So find the distance from support beyond which shear is not needed. So between 7.4 and 8.7 feet from the support, you don't need it. So we are trying to provide the stirrups in that zone. So minimum shear is needed between 7.4 and 8.7 from the support. Shear GFRP not needed beyond that. Now you know how to compute that number. That's the magic number. You have the same.
Yes.
Okay. Design tensile stress in terms of shear for the stirrup. You remember the equation we provided you with? And for the stirrup, and the value is 32 kips. The tensile strength corresponding to that, if you recall, is 24. So we are safe. That is the check for stirrups under tension. This is the stirrup spacing equation. As I told you, you cannot get an equation simpler than that. That is the required shear. That is the shear resisted by concrete. And this would give you the area requirement for the stirrups. From there, I derived this equation yesterday, if you recall. Check maximum permissible shear is. This is what needs to be checked, whichever is smaller. And the maximum spacing based on the minimum shear. This is a check, that is the max spacing. And if your stirrup spacing based on this comes out to be larger, this would control the section. But typically, this equation controls the shear reinforcement. That's very typical. And I already informed you earlier, we are not going to use a strut and a tie model in the code. Does not permit it because you don't have the what we call the yield kind of an effect in FRP. So the section is 5.4 inches. We are using a 5-inch stirrup spacing. But we already did the check, and that was the idea of this example. Okay. All right. Any questions? Maybe the audience, some of the. Any questions from the audience?
So in the continuous system, especially when we talk about the steel reinforcement and all, so because it yields, then we consider the redistribution of moments, especially in indeterminate beams or indeterminate slabs. But the similar redistribution.
No. Good question. Very good question. I don't know how many of you appreciate the redistribution concept. In steel, you do have a redistribution. Here, we do not allow any redistribution. Because being a compression mode failure, once it hits the limit state, it's going to fail. Unlike in steel, it's a tension mode failure where it hits the yield value, I still have a plateau, then I still have strain hardening zone. We do not have that luxury in this. Therefore, the code clearly states you cannot use redistribution concept with FRP. That's a very good question. There's a lot of debate on that, but they finally concluded no redistribution. And the court said that in many different locations, not just one location, 3-4 locations it did talk about. So they're alerting the designers not to get into that. This morning I was talking about connector details a little bit, not a whole lot, but try to form the reinforcement in a manner that would attempt to establish a hinge type location beyond, over and above cracking. So what does that mean? That means if I have the redistribution thing he is referring to is as follows. If I have a column and a footer, how do you form a hinge? So you provide a reinforcement from top down, bring it to the bottom, left, from right to left, likewise from left to right. And you have stirrups there, and that is your zone where hinge would form. So it's very important in FRP because of compression type failure, because of lack of ductility. It's good to have wherever possible. I wouldn't even do much research work. Maybe it's okay to have a baseline value, but I would always focus my research in terms of systems that have a hinge formation. In other words, I will not bother about testing a system going this way, this one going that way. No. So this kind of a thing is out. In any in any non-ductile system, you are better off using wherever two things. One is the formation of a hinge, the other is confinement of the material. You figure out how to confine in theory, I don't know how much you appreciate, if I have a bottle, this is in theory, if I do a compression test, this is going to fail in certain mode. If I fill this with sand and then wrap it, in theory, when I do the compression test, the load is infinity, in theory. Of course, that doesn't happen. So it will increase by 7, 8, 10 times more. That is the definition of confinement. So if you can confine a concrete, even a little bit, like why do you think the spiral reinforcement by itself, or even better yet, you confine the columns with FRP composite fabrics. I don't know how prevalently FRP fabrics are available, how extensively you are rehabilitating with FRP in the country, I don't know. But now in the US, we are really doing a lot of rehab with FRP wraps. So my message is confinement through wrapping or confinement through this type of a hinge formation between the reinforcements and the stirrups will give you this kind of confinement easily will increase at least the ultimate load by a factor of 2. Ultimate load, I said. Not necessarily the initial crack load, but on the other hand, if you wrap it externally, even the initial crack load will go up 2 to 3 times. Of course, that all depends on how many wraps you have, what is the stiffness of the wrap versus the core material, blah, blah. All those are there, we know that. Nevertheless, the simplest message is confinement in different forms. Not only it gives you increase in strength, maybe much, maybe not much, but certainly no matter what, it will give you a tremendous increase in ductility. So all our systems need to be viewed upon more from the ductility point of view to avoid catastrophic failure. Of course, we want functionality, we know that. That is where the serviceability comes into picture. For the failure, preventing the catastrophic failure, that is where your confinement and the ductility come into picture. You have a question there?
No questions.
Okay. Maybe you might ask.
On that part, that discrete fiber, what you told us.
Say it again?
Discrete fiber.
Discrete fibers.
That may also help on that.
Of course. Oh, absolutely, absolutely.
Pseudo ductility will be.
Right, right. If the concretes are commonly used, let's say, with these chopped fibers, obviously it's going to increase the ductility and this. Even sometimes the failure mode changes, then it will no longer be pseudo value, it will become a common value, That's why I don't understand, I said that 3 times today, why it didn't take off with fiber concrete. It's not all, you see, when they are delivering this with these concrete mix machines with the plastic fibers like polypropylene or whatever, synthetic fibers, I don't know why they're shying away from it.
Actually, workmanship plays a major role in preparing FRC, fiber reinforced concrete. Because the handling workability is very, very difficult, especially the larger percentage.
Even with the super plasticizers?
We have, but how we are controlling in the site is major.
Yeah. Anyway. Yeah, okay. Now, so anything else?
Yes, sir. In beams, generally after support, so generally we provide 35 times LD for the development length of whatever. So 35 times diameter or 37 times diameter. So in FRP, since we are not able to bend it in the side, so what precautions we have to take care?
This is a common question we are facing with. Therefore, they would bend in the factory and bring it. That's the common thing we are finding. Therefore, obviously, it is not as continuous as it is in the steel, but that's why our, as you can see, if I remember right, the overlap lengths are 40 or 46 times the bar diameter as opposed to 36 or 32 times the bar diameter in steel. So we have a slightly increase, about 25% increase in the overlap length due to FRP over the steel reinforcement. I really fail to understand why even they increased it, because FRP has a slightly better bond. Of course, it depends on the type of a surface characteristic. At least the sand-coated one, slightly better bond than ribbed ones, you see.
Actually, in India, we get very lesser bond between concrete and FRP than steel.
That is, I know, I heard that, but maybe again that's a quality control issue, and the curing issue, how you manufacture it. This is a two-stage curing. So if you wait too long and then roll it in the sand bed, obviously it won't stick as hard, and also it could be a resin-based issue too. You see, so again, I don't know enough here, but I can tell you from the US side, as you have seen some of the numbers I gave you, it depends, of course, on the quality, but by and large, again, nobody, I do not see people even in US exclusively using sand coated. They are using either ribbed or a combined effect of sand plus ribbed. I haven't seen, actually I put in the McKinley wheel bridge both, the sand coated and the ribbed, both I did. That's being a fairly big size bridge, I had the luxury of putting both. I put half of this and half of the other. I actually put two different manufacturers' FRP rebars in there. Okay, is there any question there? Okay, so before I go into the development type issue, lunch break? Okay.
10 minutes.
Another 10 minutes.
Okay.
Any questions from audience?
One question based on that, sorry.
Sure.
Actually, as you suggest a suggestion for overcoming the wear and tear and the strength problem also, to wrapping the columns and to enhance the strength of the existing structure due to the age and or wear and tear. So, that is with the strength, the internal stresses also they were induced by certain loads. They had the load carrying capacity of the structure. It enhances.
Oh yeah.
Wrapping.
Okay. How should I answer that? Okay. Wrapping undoubtedly increases not only the strength, of course strength increases much more, but also increases the stiffness. That is not because suddenly your concrete has somehow magically gone higher in strength. No, it is something because of the confinement. Now, that said, I said also the stiffness increase. That's not much because, okay, qualified. That's not much when you wrap with glass fabric. You could get that pretty high when you wrap with carbon fabric. Yeah, it depends on the carbon grade you are dealing with and so on. So, but yes, you can get about 10-15% increase in stiffness with glass, 30-40% with carbon. But whereas when the strength is concerned, don't waste time and money with carbon. You can, if you're strictly looking for increase in strength, glass wrap will do the job. Strength increase, not the stiffness increase. Even in the glass wrap, there is an increase in stiffness, but not much. I don't know whether I showed you, we have rehabilitated a bridge, a 42-foot high column that had a gaping hole all right across the length of the column, and then we did the rehab of that with carbon wrap. That is why that bridge is a skewed bridge, and it is in the slope, all kinds of things. Therefore, we went with carbon. Or else, for durability purposes, like big size columns, that bridge, that column is like a frame type column, not a mass column. That bridge required, that acts like a portal frame. So it is a bending issue. Most of the columns we deal with don't have that. In such a case, a glass wrap will do the job.
So coming to the application, sir, can we use this one in 10 elements like shells and FRP usage?
Yes, the answer, simple answer is yes. There was a temple built in DC area with FRP. One has to be very careful in terms of how you design, but I forgot the name. It's something close to a lotus temple or something like that. Nothing to do with your Delhi lotus, so don't get confused. There's something like that they called it, and it worked out well from a structural point of view. It did not work out well from a durability point of view because they did not understand 2-3 things. One is the creep, and the other is the UV degradation. They didn't administer adequate UV inhibitor. This is outskirts of Washington, D.C. They did that, and then I don't know what happened.
So coming to the creeps, a element is in one directional element or two directional element, how the creep is going to be affected by the movement distribution in two directions?
If it is a one-dimensional element, you have a creep in one dimension. If it's a two-dimensional element, you have a
then
creep.
In that case, the shell structure will be more effective compared to that.
Again, from a stress distribution point of view, you need to be thinking how the forces or stresses are distributed, So that is, from deformation point of view, I think the deformation is a follow-up of the stress, So I'm not sure I am able to answer your question fully, but it's a two-dimensional problem. I'm trying to, or actually it may even be a three-dimensional problem.
Even in plane forces and shape.
Right. If you can convert the bending forces into axial forces, you're in business, you see. What is that? What did I mean by that? That is, the old arches are almost all are axial effect type thing compared to, so they essentially converted the bending into axial effect. So if you can convert the membrane effects, for example, that we deal with, are all in-plane forces, then if you can convert that into tensile forces, you have better luck with creep than compression forces. Yeah. That's why I'm hesitating to answer your question. I'm thinking while talking. At any rate, I don't want to give an answer, but it should work out if the forces are turned into in plane forces. Yep.
So it's one of the we will elaborate.
Okay. Any question? Any questions?
No questions.
Okay.
So again, we will assemble at 2 o'clock.
I'm waiting for the. Okay. So here we want to talk about development of bars in tension, compression control, or a transition. You want to reduce that a little bit, the size? Yeah, good. So what we are looking at is zones A, B and A, C, where you are talking about the development length. The clear cover is 3/4 inch. This is the development length for number 8 bar embedded in one-way slab to develop full moment capacity. So you can see the bars. So the values. Okay. Again, the drill is same. F sub FU is 80 KSI or 85 KSI depending on 0.8 or 0.85. The effective depth is clear cover minus half the bar diameter, 14.75. And the rho F. Here, how do I find the area of the bars? So, as you can see, we are looking at a unit width or a unit, meaning 1 inch width or a 1 foot width. That's a very standard approach.
Yes.
You keep it very simple. So that is what that is. So you're talking about the bar area per foot length of the slab. So from there we found the rho F, and then compare that against the balanced value to understand whether that is high or low. And obviously rho F is twice that of rho balanced, therefore it is compression control.
More than 1.4.
Right. So you can see the tensile stress in the FRP based on that standard equation we're talking whole day today. That turns out to be that way below the rupture stress of the bar, which is 80 KSI. So the important message of this slide is find the stress in the bar which must be less, otherwise it's not a compression control.
Yes.
That is the point. If you got something higher than 80 KSI, something wrong with your computation, That's what we did. So again, please note, these equations that are given to you here are empirical in nature. And that is the code equation. I forgot to mention the code equation number, but that is the code equation. And I defined what is C, which is the minimum of the cover, center spacing divided by 2, or this should be less than 3.5 dB. All these, you might be wondering where we got it. All these came from testing procedures. That's what I keep saying, empirical relationships. So from that, The C value is 1.25 inches. The bar diameter is what, number 8 bar. So we can substitute it in there, and the required, based on that, the required LD is 63 inches. So somebody was asking me, Indian code has 36 or 32 times bar diameter, and you can see this is much higher than that. I need to qualify. What this 36 they're talking about is with respect to steel, and with respect to composite, it's almost 60 times. That does make sense, implying that when we run the tension test, we are finding you get a better value with a larger gauge length as opposed to shorter gauge length intent. So that falls in line, and this equation came about in the sense of empirical experimental work. Most of this is done in Canada. Most of that work, yeah, they are doing pretty good job. Okay. So the dB is 1 inch diameter bar. That's compression control. In the tension control, find L sub D for the inner 2 number 8 bars at a column face. Obviously, near the column, it's a tension at the top. That's what we mean. So 2 number 8 bars are continuous along the length of the full beam. If you remember, you have seen that about 6 slides before. And what is given is 4,000 psi concrete, 80,000 psi, before correction, 6,000 ksi, modulus, that is the depth, effective, beam size is 12 inch by 30 inch with a 2.5 inch cover, and the side cover is 1 point, that's given. So it's the same thing. We have a total value of area, 4 times 0.79. There are the 4 bars there in that top of the column interface, and that is 0.0096 rho F, and rho F or rho B is very close to 1, but still slightly less than 1.97, 0.97. Therefore, we call this a tension control. Yeah. And again, this is the formula. We substituted all the values. So we got a much higher, previously it was about 63 inches, now it is about 79, 80 inches. So again, that falls in line with what you expect as a common sense type thing. The numbers you may not know, but it better be higher from a tension control over a compression. So this is a two-way action shear strength by concrete at interior column support. So what you're looking at is an 18 inch by 18 inch column with an effective shear transfer area is 18 plus D. That's a very standard, everybody accepts it based on your 45-degree angle type. That's where it comes from actually. So again, these are just some numbers. We are keeping it consistent. That's about it. The plate thickness effective is 6 inches. Probably the total depth is 7.5 inches. The punching shear without any shear reinforcement. As you know, just reminding you, this is 0.75, and the shear strength of the concrete is, there are two formulae they are using. Here you can see this is one of the two given by the code, and the K factor based on that quadratic equation. We have already defined, if you recall, the rho F value, and NF is close to 1, and you substitute various values there, and what you get is 0.18. You keep talking about KD value in the range of 15-16%. So sometimes you can run the computations with these standardized numbers like K of 0.18 or 0.16, that type of thing. And if you go back, the B0 is the perimeter of the shear area. That area, that is the shear perimeter, and that's what we are showing there. B0 is 4 times 18 plus 6. So that 4 comes from the perimeter. The punching shear is given. The equation for the punching shear was given in the earlier slide right there. And that is the equation we use. So the concrete capacity to resist punching shear in this case is 49 kips based on that empirical equation. So that's a very simplistic approach. I will give you a more detailed approach tomorrow, but now let's talk about what's a slender column versus a non-slender column. You know the difference between the two?
Again, depends upon the usage.
A non-slender column fail in compression. A slender column buckles. That's the difference. Before we do anything with columns, few minor things one should know. These are at least 2 or 3 items. One of the items is that how do you separate the slender column from a non-slender column? That's one. If it is a slender column, what is the controlling factor, which is pi square A over L square, Euler's equation for slender column. The third thing you need to know is boundary conditions of the column. The L effective pi square AI over L square, that L is effective length. And typically people say that L over R below 24, 27 is non-slender column. In that range. Again, don't take that 24 as a gospel. It's not. And if you go beyond 27 or 28, then it becomes a slender column. Okay. What is R? Radius of gyration, which is square root of I over A. So those are the few minor things one needs to know. Again, I'm going to repeat myself, and I said this here somewhere, that very, very important for this. May agree, may not agree. Ability of reinforcement to resist axial forces is neglected, unlike in steel, which results in lower GFRP column capacity. If you look at steel, for example, I'm just using that as an example. If you look at steel and try to establish the capacity, axial capacity of steel column, normally, as I told you before, on the lower side you have 2% of the area on the lower side of gross column area as the steel area. Okay. Normally we use about 3 to 4% of the gross area. As I told you this morning, never exceed 8%. That's a rule by the code due to many reasons. Keeping that aside, normally when you design a column, you're talking about 3 to 4% of the gross cross-sectional area. What I want to say here is important. The force is, they always have some reduction factors. I'll come to that a little bit later. But the message is, force, you're the one asking the question. Force is the stress times the area. Now, here we have two different kinds of stresses in steel. One is 4,000 or 5,000 psi concrete times the area plus 3%, 0.03, let's call it, times the steel area times the steel stress. So we already said the area is about 3%, means 0.03. But my message is the amount of stress that steel can take is about 8 to 10 times higher stress, I said. 5 to, say, steel is 40, 50 KSI, so it's about 10 times, you know. So what am I trying to say? If concrete as a gross section takes 100 units, corresponding steel is taking 0.03 times 10, that's 30%. So you have a reasonably substantial amount of load carried by steel. So that is in terms of steel. This is where the conflict comes here. But here they are saying we are completely neglecting the amount of resistance offered by GFRP. On one hand, when you're doing all the computations, you're telling me that I'm going to go up to 60 KSI, but here I'm going to assume it's going to only take 5 KSI, or whatever that concrete F prime C is. Now they are going to argue that there is a micro buckling of FRP unlike in steel. Okay. Which is fine, that is true. There is a micro buckling, we don't deny that. That's the reason we are not able to come up with an ASTM procedure to establish a However, the micro buckling is nowhere close when you are talking about the service loads. I mean, far from it. You understand the argument now?
Yes, sir. The micro buckling is
at the tail end of, exactly. Maybe it is beginning to buckle at 70 or 80%, but your service life is only at 20 or 25%. Now you got the point why I keep saying the buckling issue is an excuse. I mean, I shouldn't say it that way. Maybe I should say that they don't have the data to prove it. So I'm asking him, he's going to do the work to put a gauge or something and establish how much load the rebar is resisting.
Even in the column testing also, the cracks will appear almost at the 85% of the ultimate curve.
Exactly.
Not at the 60 or 70.
That's right, because it's under compression. One of the good parts is it is under compression. Exactly.
Even the micro buckling will not occur because the concrete is intact with the fiber.
So why did they not include? I am guessing, I don't know, I wasn't there, because they don't have experimental data. If you have an experiment, this is where you all can fill in the blanks that are left open by us. So we don't have the data. You all have the money, can generate the data, and you have the brains to do that and challenge it. Unless you stand up and challenge means don't take my word wrongly. I'm not there to fight. It's a convincing argument where we believe it is right, you know. So I believe it is going to be, for example, 60 KSI for GFRP, just like steel. They should be able to take that into account. All right. Now, that said, there are two reduction factors for a column capacity I'm going to talk. One is obviously a reduction factor corresponding to any of these materials, which is about 0.8 or 0.85. But the most important reduction factor is due to non-collinearity of the column top and the bottom. I'm not saying it is there, even though you call this a concentric column, we are talking about the slight bending, and they use 0.8 factor for reduction. If it is a tight column, they use 0.85 factor of reduction due to that non-collinearity if it were a spiral column. Okay. Some of that I will show you. Oh, it's right there. I mean, I said I'll show you. It's right there. So that factor 0.8 comes from that. So you can see, again, one can debate whether this factor is 0.8 or 0.85, but it's in that range. It's not 0.6, it's not 0.95, you know. And it's very difficult to get a perfectly collinear forces acting from top to bottom in any construction. That is that reduction is all about. And especially if you were, there is that, if you remember, I used the word 10% thing, you recall? If the applied load is less than or equal to 10% of this equation, that means you don't have to worry about any bending related issues. Okay. So if somebody can test it and prove that the bar is taking adequate amount of loading, I think it's well worth it, you know.
But even the rebar, if we consider the compressive strength will be almost, we are getting 60% of the tensile strength.
Correct.
So
Correct.
we may include the bar, resistance.
Look at it this way. The bar, let's say we're dealing with 100 KSI, then we reduce it to 90 or 80 KSI. Now you say it is, reduce it to, instead of from 100 to 85 or 80 to 60%. Still it is equal to that of steel. That's my argument. So there some improvement can be made. Okay. With ties, it is 0.8. With spirals, it is 0.85.
Sir, in the previous slide, where did we consider both the reduction factors? where are the separate reduction factors? Like for the material and another
0.8 and 0.85.
Right there. 0.8 and 0.85.
0.8, the former 0.8 is for
Is a general reduction factor for because of our basic uncertainty. That's a very standard reduction factor for columns in
eccentric case.
Accidental eccentricity.
yeah, accidental is the right
You
word.
can say initial imperfection.
Imperfection. Yeah, yeah,
Our one is accidental eccentricity.
yeah. You can, yeah.
Sir, you think that this reduction factor is different for spiral reinforced?
Yes, the values are a little bit different, meaning, as I told you, 0.8 and 0.85. That's also coming from the steel code, except that variation is attributed to the confinement effect. So if you remember, have you done a concrete design course? If you remember, this the tie spacing should be less than 3/4 of the minimum dimension. You remember all that? Where is that coming from? Because when the crack forms, God forbid it won't, but even if it does, that crack is going to cut through the two contiguous ties, whereas you don't have that problem with a spiral. And if there were a crack. Okay.
Sir, but the crack will also across two consecutive pitch.
Huh?
But in the case of spiral, also the crack will have to cross two consecutive circles.
Yes. But the confinement effect is much more effective than in ties because of the continuity aspect of the spiral.
Who stress is continuous.
Right.
Spiral.
Correct. Okay. So I already told you that 10% thing, if your PU is not exceeding that 10%, then you don't have to worry about if the design comes into play only when PU exceeds 10% of your concrete stress times the area, which is the force. Nominal axial tension is standard equation, and AF min, whether you have any force or not or whatever, so you are talking about a minimum of 1% for columns. You must provide. Again, very similar concept to bending. You remember with the AS minimum we talked about? I told you how the FR rupture modulus based on that first crack, so you don't have a catastrophic failure. They call it here passive yielding. That's what they call it. GFRP in tension must be limited to, again the same deal, 0.01. So these are the assumptions. Again, you can challenge that 0.01. This is again for very high bar diameters, where if I assume this to be a modulus of 6 million psi, this 0.01 to 6 million gives me 60 ksi. But if for columns we go up to 10, I think we limited it to 10. There was a debate of going to 12 number size. Number 10 means 1 1/4 inch. As the size increases, they're worried about FFU maybe going below 60,000 psi or 60 ksi. So if that were to be the case, so some of the codes, I think even we give the load, then you divide by the area, as opposed to giving you just one stress value like steel does. So we don't do that due to the shear lag issue. So the closed loop tie spacing is given to you there, not greater than 12 times the longitudinal bar diameter, 24 times the tie diameter, or smallest dimension, whichever is smaller, and obviously it has to be larger than 4/3. That's a pretty standard common sense. Minimum tie diameter, if you remember I told you, number 3, we don't have number 2, but we don't exceed number 6. Typically, that's where we are. Minimum overlap is 20 times D sub B, or 6 inches. Satisfy the stress up to 0.005. This is again an empirical issue. So the F, or the stress, and E, you were telling me the value is about 60%, for example. We have taken approximately 55%. Okay, but likewise, our compression modulus is, this is fair, extremely fair, 80%, which is, that's a, I don't know, is that what you're observing too? But what they did not observe, that is the problem. What they did not observe here is, that is true for an individual bar, but not a bar confined in concrete. See, we are talking about a realistic scenario. So that's why I keep encouraging you to put a strain gauge on the bar while you're testing a column.
Actually, we have tested this compression bar, only one single bar with different L by D ratio. So with L by D ratio 10, we observe that the E value is coming very less. That because of certain other thing, because since it is higher, so we are calculating for load deformation, right? So that buckling issues will come. But in concrete, it will not happen. So in concrete, it is.
That's my point. That's exactly my point.
Actually, the specimens should test under the triaxial pressure.
Right.
To get the
Real, correct. But again, if you're going to test a concrete with FRP bar and put a gauge on the FRP bar, then you get a very realistic value. And what I'm saying is, those numbers will be much higher than that. So I don't know how you place a gauge. What we did, we leave a little styrofoam plug, and then we have a gauge, and then we bond it. We have a styrofoam plug, and then after concrete is poured, we dig it out and attach it to the wire. Now we have a wireless gauges too.
No, so we use with sandpaper we used to clean that place, and we have one very good kind of glue. So we just put it and paste it on that portion, so that wire will come out.
Yeah, well, you can do that. But now we are getting a wireless gauges. You can put it there and send a signal. You will get an answer. That's much easier. When I was a student, I put all these gauges we didn't have the wireless gauge at that time. So we used to put about 20 gauges a sample, to understand the whole crack profile, not just one location here.
Profile also you can get.
Right. Top to bottom. You see, this is particularly important in your case because you have end effects where you are applying the load, you have a much higher load concentrations than the ones in the middle, or mid 70%. Top 15, bottom 10-15% is far more severe, than the mid 7. So you can get a good profile of that. Anyway, that is the discussion. Which one? You mean this one?
Yes, sir. What is the
Wait. FFD is the, no, all we are saying is FFD is the ultimate tensile strength of the GFRP. That's all we are saying. So that is, we already defined that in the sense that when you do the tension, then you have some reduction factor. After the reduction factors is what that FFD is. Okay.
What is the capital F in the starting capital F? No sir, in the
So that in the equation, FF compressive. You're asking for that?
yes.
This one?
No. They're starting FF compressive.
That is
That should be small. That should be small e. That minimum of cylinders like.
Young's modulus of incompression.
This is the Young's modulus of the under compression.
Compressive, he's asking for that.
Yeah, that's compression. See the tension, okay, I thought you already understood. The tension values are different from compression values. It's not like steel. And remember another very important, when people keep measuring these, I hope he does, even for steel you have some ASTM procedures of how much is this aspect ratio, meaning the length versus the diameter. There it is a little bit more consistent than in FRP, because you will never ever get a consistent result in FRP in relation to length of the specimen versus D, because it is going to crush very easily due to Poisson's effect. That is why you doing the experiment in a confined environment, like he is talking about some triaxial machine or in a concrete environment, if you do that, you get a more accurate result. So this is
term, sir, it is ultimate compressive strength of GFRP.
right.
The first
But you mean this one?
The first term, sir, in the line. FF compressive.
Right.
Ultimate compressive strength of.
Okay. You may get an ultimate compressive. For design purposes, you have to make all the correction factors to define that. That's what we are saying here.
Design compressive strength.
Right, design values. These are not actual values. So again, I don't think people fully understand, appreciate. Let me repeat myself. If I test 10 bars, let's start with the tension, then we go to compression. If I test 10 bars, I get values, whether it is steel or it is composite, doesn't matter. I get values falling all over the map. Meaning, suppose say I'm supposed to get a yield value of 60. Let's say that. When I test 10 bars, I get 58 for one, 64 for another, 59.2 for third, like that. When I average it, I'll get 61 or whatever. So we declare this value is 60. Okay, that is the average value.
Average of the ultimate.
Average of all the 10 tests. But that is not what they report as a minimum guaranteed value. So that minimum guaranteed value is the average minus 3 sigma. 3 times sigma. Assuming it is 8%, some number like that, or 6%, 6.5. So that multiplied by 1 minus 3 times 6.6, that's 0.8. Therefore, what they report guarantee for you is 0.8 times that average. So you see, that's the second one. And the third one, when you're ready to design, you're going to multiply with the CE factor and other reduction factors. So that's how you need to. So you don't even know what the average value is. What you know is the average minus 3 sigma value. So I think there's a big confusion about all. It's even more difficult if you are going to look at it from the 95th percentile point of view. Yeah. So that gets it even a little bit more, perhaps more accurate, they say. Again, I didn't do enough work to say that. I'm only parakeeting what I hear people saying. So that is why you need to have a good clarity of what you're doing. Is that clear now?
Yes.
So that is what we are discussing here. I think that's where the confusion is. Column stiffness modifications for linear analysis. What is that? Okay, what is a linear analysis? What is a non-linear analysis? A linear analysis is that we are not accounting for P delta type effects. If you account for a P delta effect, that becomes a non-linear analysis. Give you an example. I'm sure a lot of you have heard Sears Tower, right? Sears Tower in Chicago. At one time, not now, was the tallest tower of the world, and the horizontal drift of Sears Tower under heavy wind conditions is approximately 14 inches. Not a whole lot, really, 14 inches from bottom to the top. It becomes one heck of a lot of a number when you multiply the P times delta, right? Delta is only 14 inches, but the P is zillion tons. That makes it drift more. That can be higher, the drift, due to P delta than just due to the wind as a first order analysis. So that gives you a perspective. Okay, now what they are showing you here, please look for linear analysis. For steel bar, I-beam, 0.35 Ig, slab is 0.25, where Ig is the gross moment of inertia. Now they give you a more accurate formula for, this is all for steel, not for GFRP, right?
Yes.
Now please look, the GFRP value, look at this, 0.7 versus 0.5. So obviously there is a penalty function here when it comes to GFRP compared to that of steel. So the moment of inertia of GFRP RC beam, again, look at how much of a reduction we are talking about. If you remember, for bending cases, we used what? You remember what we used for bending? 0.22. It is slightly higher, 0.25 here, because there is a column compression load. Unlike in your bending, we have like some kind of a pseudo pre-stress effect due to column compression. That's why it's a little bit higher. So this is, again, the egg or the chicken type issue we talked yesterday. These are the numbers we are going to start with for your linear analysis due to column frame drift. So you can see I column with the GFRP. These are all, again, empirical values. There is some theoretical basis for arriving at it, but by and large, they reduced it to some kind of an empirical value. So all these are given. Average, as I said, if you remember, the average rho of the steel percent is about 2.5%. In GFRP, it is of the order of 3 to 4%. This is an average. Yeah, typically we don't exceed 2.5 in steel. Once you exceed beyond 4%, you are going to get into the crowding of the bars in the formwork and inability to avoid honeycomb effects. And it's very important in columns, make sure that you don't have a honeycomb effect, you know. It's important everywhere, but it's more important there. But anyway, my message is for this, these are the kinds of I values or the stiffness factor values we are going to be using for the first order analysis. Okay. KL over R. So I need to differentiate the swayed column from the unswayed column. So neglect the centerness effect in swayed columns when KL over R is less than 22. So for unbraced column against sway, KL over R is 17. And we briefly talked about it yesterday. Somebody was asking me a question about it. And these are this is the ACI equation is this, that is kind of modified in this fashion for GFRP. This is the steel. You can see the reduction. Obviously, that is coming from lower modulus of GFRP. So, using that as a backdrop, now let's do the example. GFRP column, there are two things I'm going to do. I'm going to talk about a column capacity example. Then I will be talking about axial bending interaction example. The two examples I will be dealing with. Here, a very simple column, 12 inch by 20 inch with cover of 2.5. We are assuming AS and AS prime area of FRP in the tension side and compression side are equal. AS is for the tension side, AS prime for the compression side. They're equal. For number 9 GFRP bar, number 9 bar is 1 square inch. I kept these numbers same. Therefore, the rho F is 0.038, obviously much higher than the rho F balance. It's a compression control. So if I do that, you can see the balanced value. This equation doesn't change as we talked about it this morning. That's what that equation is. And the balance value is 0.01 compared to 0.038. So they want that factor 1.4 is given to make absolutely sure you are not in any gray zone. 100% certain you are in failure under compression. That's that factor.
Always over-reinforcement design.
Correct, always. Okay, now the section is compression control. Again, I repeat myself, GFRP in compression has same properties as that surrounding. That is where we are debating. That's where we need, somebody needs to stand up and challenge it. So here, from the force equilibrium, Here are your two factors, sir. You can see 0.8 or 0.85. I'll leave it to you. So that the compression side must be equal to the tension side, and this is the strain compatibility equation. From here we solve for that square. There's a 2 missing, I guess, here, FFT square missing. So my message is that number is less than 60,000. When will it be less than 60? Only when it is in a compression failure. Otherwise, it will be more than 60,000. And you call it a compression failure, get more than 60, there's something wrong. So then you solve for FFT. So the capacity of that for bending is 2702. The nominal axial value is given to you there, 0.854 F prime C. This is the area under compression only. That's one. This is the width, that is the effective compression zone, KT times D, right? That one? If you remember, if you go back. Yeah. You multiply that with the beta 1 factor. You remember that? That's how you get that. Where is that? That 4.32. There we go. 5.08 times 0.85. Okay. So the eccentricity, the max eccentricity is 15 inches for that column. Okay. Next. Tension control. I reduce the area of FRP to 2 square inches, and you can see that, and then rho F over rho FB. The computations are identical as before, except the areas are reduced to half, and that's why you see it's a tension control. That's the equations, that's the one we did this morning. That's an unrealistic number, the E value, right? So that is tension control. Okay. So this is how you establish the capacity of a column, both in terms of compression control and tension control. If you look at the tension control, you see you got, say, 1896 or 1900 inch kips. In a compression control, you got 2700. Stop and think about it. I kept everything same except doubled the area of GFRP. How much increase in cost do you think I had in terms of the overall column type thing? But I got a 50% increase in the capacity. So for pittance, for about few dollars of extra reinforcement, I got 50% increase. So as a designer, you need to optimize the response in this manner. So treat GFRP as having the same strength and modulus. This is for the column analysis and design to establish PM curve. What is that? Load moment interaction curve. I don't know, some of you may not know what is a load moment interaction curve. That's how it looks. What did you observe from that? Most important thing that one must be able to observe with a trained eye is that that point is constant, which is not true. That is from the assumption. See? No matter how much, how high, how great FRP you may have, but the core assumption is telling you that. That is the fallacy. Now, if I keep increasing, if I keep having some amount of moment inducement, then the load is going to decrease. For steel, you have PM diagrams somewhat parallel to each other. Not exactly, but something close to it. So that's the difference. I'll go back. Okay, now we are talking about design, right? So there again, we are talking about load factors, load combination factors, and all that good stuff. And that's what you are going to see here. Case 2, case 3, and all that stuff. Here is the load, dead load factor life. This is for a particular load combination. Load case 2 or load case, this is a combination. That's what we mean. For load case 3, this is the earthquake combination, for example.
Yes.
And this is a no earthquake type thing, and that is dead load, factor that, live load, factor that, wind load, and snow load. If you remember, I said most of the load factors are above 1. But here, when you get into the combination, it is that 1.5. Why? Because in combination with wind, snow is not going to be 100%. In combination with wind. That is the key word. You have, as I gave you, there are 8 or 10 load combinations here to check. Okay. And there's a load combination 3. So this is a PU. This is given. Inch kips, 15 and 20. MU1 is 600 and 700 inch kips. So step 1, find the column size. I gave you the bending moment or axial load requirements. So based on that, we are trying to find what is the size. That's right. That's the design. We are away from analysis now into design. So Pn max, if I have 0 moment, that is called Pn max. Means, what is a 0 moment? Sorry, I'm sorry, I'm going in the wrong direction. That is the 0 moment. That is Pn max, which is a very simple thing to compute here, due to we don't even have to worry about the area of GFRP in compression, so it's just a one-step deal to establish that point. Then it gets complicated to sweep through this curve. So that is one step I said. You remember that? Pn max is 0.85. Pn max is 0.8. P0. And 0.85 F prime C. So from that equation, including the load reduction factor, that equation results in, for that load capacity of 600 kips, a 271 inch square. A 17 inch by 17 inch column has 289 inch square. Check for slenderness effect. This is a thumb rule. What we are assuming, if the column has a bending column with critical buckling load, is roughly 5 times, that's a thumb rule. So this is the effective value between the column center to center is 18 minus 2 feet is the beam depth. So that is what you get. The K effective, we will talk about that later. I'm just assuming for illustration purpose, K effective is 1.5. So this is the effective value defined by the code. P critical pi square EI over K L square or L effective square. So pi square 4, 106. This is 10 to the power 6. K effective is, we're saying 1.5 or 1.9. And this is the 5 times. You remember I told you that's an empirical relationship, pi square EI over L square. And so the I value is about 26,000. So for a cracked section, we are going to assume 5 times the given load. That is where that 5 comes in. This is the given load after adding all your load factors. Okay. So that is the K factor. So the K factor, there is a way to determine the K factor. You have that bar chart. I don't know how many of you remember. Do you remember that? I don't think you do. I'm not sure I have all that. There is a special procedure of how you find a K factor in any kind of a complex multi-story building. What is the... Huh?
For braced and unbraced.
Unbraced, right. But I don't know how many of the people here know, I'm not sure. But let me leave it. No, I know. I don't know. Some of them may know, some may not. So anyway, all I want to say is there is a special approach of finding the K factor for a frame that is one set of what is it? Bar chart, like you call it? The K's are here and here, lower and upper for unbraced, and then one for braced. Okay? So we have that very standard. I thought I put it, but I'm not sure. At any rate, so the gross value required is 5 times pi square EI over L square type thing. That is the message. You found it? Yeah, that's fine. So, based on that, that is the moment of inertia requirement. From that, we have, if it's a square column, it is 4th 112 BD cube, B is equal to D, D4, that's where that 12 comes into picture. That is the 4th root of that multiplied by 12. Okay, so this is an approximate starting point to start designing a column for the given load, in this case, of 600 kips. You found it? You found it? Okay. Yeah. Wonderful. You can go ahead and explain. We use a slightly different approach, so you can see the effective K values, as you can see there. So you want to explain that?
We have beta 1 and beta 2 factors. So based on the conditions fixed and hinged. So this is.
I think the only difference is on that Q value if it is less equal than 0.04 in the top, up. First, and I say that Q formula is given and the Q less equal than 0.04. That is, I think in SI it is 0.05. I think.
We have a slightly different kind of chart than this, but that's neither here nor there. You follow your own approach in terms of establishing the effectiveness of the beams connecting at the top, including the slab, and the effectiveness, that K factor effectiveness of beam at the bottom. So that's all you have to do. So that's a very standard approach. Okay. So we arrived at a column size as a starting point. Step 2, find slenderness aspect of it by neglecting the slenderness effect, then conducting the first order analysis. The first order analysis is without the P delta, and also is based on empirical values that we gave you. What are the 5 times that? Then we have reduced I values. You remember? Yes. So that is the key word. So you will see that. Please see that here. So KL over R, that is the end constraint. They're all defined for you in chapter 6. The first order analysis, this is what I'm talking about. The reduction in the gross moment of inertia for the column is 0.4 due to bending effect resulting in cracking. At the service level, this is about that. This is, please note, this is a guide. For a T section, 2 times moment of inertia of the rectangle with a flange. That's a guide. So the gross value of the beam, 112 BD cube, right? So keep it so simple. And then you find the reduction. This is again as per ACI. The cracked section for the beam, 0.15 times that. For the column, that. So this is what I'm talking about. Without going into the chart, this is one way you can establish the stiffness effect. That's what there are many ways to skin this cat. So this is one way to skin it. The column above, column below, beam left, beam right, that is your exactly. So the phi B, find joint relative stiffness below column. Again, based on the previous approach, 2.4, the alignment chart, there are, so once you establish sigma A for the top, 4.06, sigma B for the bottom of the column, 2.49, there is an alignment chart similar to what you showed. We have a slightly different alignment chart. That chart give me 1.9. That is your effective length. Obviously, since the top and bottom are partially fixed, you must get a value lower than 2, higher than 1. That's what it is showing. So, the slenderness effect, I over A. So, what does this mean? This means you cannot neglect the slenderness effect. check the frame for sway or non-sway. Maybe we should stop. Oh no, we have some time. So find if the column must be analyzed as a sway or a non-sway. Again, there's a guidance given in the code. The load combination is provided there as per the code. So P sub U, sum of all factored column and wall gravity load at floor are considered for combination 3. That's found to be 200 kVs, while sum of the factor loads is 18,000. These are given to you. If they are not, you need to find out from the analysis. This is only, I made that very clear. All the numbers are only for illustration purpose. This is a fictitious number. So the story deflection, what is a story deflection? That's the drift. It is primarily dependent upon the horizontal loading. So it is something very close to, you can see, V is the force, L cube over 12 sum of the EIs. That is the equation given by the code for the first order analysis. Because of cracking of the joint, full fixity is impossible, hence factor 3 as opposed to 12 is used in the denominator as estimated deflection. If there is no crack, it will be VL cube over 3 EI. PL cube over 3 EI. Remember the cantilever thing? Good. Because of the cracking of the cross section, it is PL cube over 12 EI. But EI is a combination of all the columns that are resisting the lateral force along the whole story. So, EI is given. So the delta is 0.33 based on that equation. Again, that assumption is from ACI. This is what they call stability index. This is the PU times the delta. You see that P delta effect now? But this is empirical, mind you, not second order analysis. That is the difference. So in a convoluted manner, we arrived at the delta effect in a very, very convoluted manner. And that, again, this is ACI suggested procedure. Please look at section number 6643B. As per the ACI, for non-sway criteria, initially evaluate as per, which considers the end moments from P delta and evaluated as a non-sway frame. Step 4. Now, what is that? We are accounting for P delta effect here in a indirect manner. That's what we are doing. I wrote here, M1 is the first order moment from the gravity. M1S is essentially due to the lateral loads. So that's what we did. So all this anxiety is to establish these two moments. One is coming from the gravity, the other is from the lateral load effects. That's what we did. So one option is to come up with this A, and B is what we have shown you there. So the delta S, so not very close to option A of 1.16. A more accurate analysis will give you a closer result. From option A, we said that's not very close, but one can go with it if you want. The second order effects, oops. So as you can see, the moment capacities are close to 1.4. End moments from the second order effect exceeded by 5%, which implies neither criteria is met, hence analyzing as sway column is met. So with all this, first we are establishing that the column is a swayed column or an unswayed column. So we establish that as swayed column with all that effort. That's the procedure. So if you look at the example of PM, I'll go over this tomorrow, but let me go over this in a broad brush manner today. So this is the given compression side area is neglected from GFRP for the PM diagram construction, and the tensile strengths are all given. The strain compatibility is given. I'll go over it again tomorrow. So I'm going to find the capacity of P for different C values. The compression block values of 4 inches, 13 inches, 22 inches, things like that. That's what I'm trying to do. Correspondingly, I'll go through this tomorrow again, but the message is that what is the capacity of the column with reference to bending moment when I have a C factor of 4, that is the C factor there here. If this C is 4 inches, if this is 16 inches or whatever, 22 inches, what is the corresponding bending moment? That's what I'm trying to find out. So, and I did that. There's a procedure, I'll explain that tomorrow, and you can see, I'll explain it carefully tomorrow. With 0C, you have 1958. For MN, for 4 inches of C, my moment is 48.58. With 0C is 0 moment. For 13C, 7486, 22.57. So, I'll explain that tomorrow. When I plot it, that's what I get, which is very similar to the idealized PM diagram that I showed as a very first or second slide of this example.
Sir, how did we decide the critical points? 0, 4, 13, 20?
No, I just picked some randomly, some points, like you could pick 3, 12, 20, not 4, whatever. I just, to construct in this random pick, what I might miss out is the peak value here. It's easy for me to find this value where P is 0, easy to find this value where M is 0, and the intermediate values, if I'm not careful, I may miss that peak. And then you have to multiply this with appropriate phi factor, exactly. And that reduction factor varies depending on the fact whether this section failed in compression or tension, whereas when it came here, did it fail in compression. So that is this is not the true actual design number. The design number is PU, not PN. So PU is with a phi factor, which that is going to be under this curve, within that curve, I should say.
So this PM diagram is not depending on this compressive strength, the founding or strength of bar.
Repeat it again. I didn't catch it.
Diagram.
Yeah, okay, I got
Is there
that.
any relationship to the strength of concrete and strength of steel?
Of course. Certainly, the Pn values or Mn values are dependent upon concrete strength. As the concrete strength increases, both will go up. That's number one.
So it's also considered for developing this.
Oh, yeah. I mean, I will explain that tomorrow. Every step of the way, F prime C is a function. See? Every step. Or whether it is C is 0, C is 4, 12, or 22, it's a function of F prime C.
Yes, sir. It was mentioned in the previous slides.
Right.
More previous.
Here. That is a function of F prime C. Pn is what? Remember? F prime C function. Very early on. I'll explain that to you tomorrow. Please look here. What is that? Concrete strength. F prime C. So it is a function of F prime C, but it's a highly convoluted approach, and you do need this for design of, whether it is numbers may be different, but the procedure is same, whether it is a steel or FRP. It is a little bit more involved with FRP because of there is a couple of more complicated empirical equations, but the philosophy is same. The reason I keep saying that is, don't be scared about it. So most of you are aware of how to design these with steel, so it's a matter of tweaking it for FRP. So that I'll repeat this tomorrow. So any questions after this? We are exactly 3:30. They want to ask questions from now for the day.
Maybe participants can try some of the examples from 1 to 4 by using SI units.
Yes. You can try that. And if you have questions, you can ask me. That's a good homework, he's saying. So,
because, in India, we are more SI units.
Right.
We are very comfortable to understand the behavior also from the SI units.
Sure. Yeah. Another thing is, I will leave my book. I have another copy of it, but later, that's after tomorrow. But this book also has examples, and I think, if I'm not wrong, there are some examples in SI units. This is a workbook. I'll leave it with the Professor Prakash, so you all can refer to it, or if you have any questions, communicate with them. But tomorrow I'll go over it. I just broad brushed it today just to give you how a PM diagram is constructed as a very basic fundamental thing. I'll repeat it tomorrow. Any questions? That is why I attempted to provide as many details as I could, both in terms of numbers and also in terms of explanation. And all this would make a much better sense if you read through these examples with the code next to you. Without the code next to you, you may be a bit confused.
There is a slight confusion, sir. There are many, the reduction factors are being applied at many steps. That's a
Yeah.
The design is to be kept as an engineer safer side. That's why we are doing the constraints.
According to the Indian codes, the reduction factor is usually implemented at 1 or 2 steps generally. They combined all the types of reduction factor in one number and just multiply it once. But here,
that leads to a higher penalty in terms of, so you get a more conservative design. But here, by having these factors, so you have a choice where you want to apply some factors in a given structure. If you may not need the same reduction in a different kind of a structure.
That is more concepts now.
Right.
You understand?
In India, the column design, if I consider, so we start with 0.4 into AC into FC plus steel. But here 0.8 into 0.85.
Correct.
The point 447 is also coming like it's because we first of all we use the tube strength. We convert it to
cylindrical.
Then we multiply the factor, which is 0.85. That is. From there it is coming to 0.85 and then it is 0.8. Then 1.5 we divide the material safety factor by 1.5, so it comes to 0.447. For column again we reduce for the accidental eccentricity.
That's a lot of penalty.
Yes.
Yeah. But in spite of it all, why your structures are not as durable? I don't follow. Is there some material issue?
Yes, actually one thing Professor Surya told in morning, that is water cement ratio. It's very hardly controlled in normal.
Well, I thought you all said now we are controlling it with 0.4.
Yeah, but in lower level, or say like not that much supervised constants.
I'm quite surprised you were the Bombay, what is that bridge or road, you have it in the sea? You know, what do you call that thing? Yeah, there is some kind of a loop or a diversion. I do really wonder how long that would survive. You know what I mean? It's all right when it is new. Come 20 years, what happens?
Already it was 15 years old, I think.
Somebody told me one of the bridges failed I mean, they don't tell you. Failed means whatever the excess deflection, they fixed it, but if it's only 15 years old, imagine.
So the margin in the contract is also issue in India. It's like if someone applies for a construction tender, then the rate margin is too much.
Too small.
Too small for the contractor.
Too little. But the question one has to ask is, you need to increase the margin. You know, after all, these are supposed to be the iconic structures for long-term productivity of the country, right?
At material level, the production is good. The provisions are quite nice.
But the execution is bad.
The execution. The problem is that the execution.
But this is the general procedure we apply.
There is a request,
Huh?
actually, that you can keep some more emphasis on deflection and crack width, because we could not understand that properly. Yes. Deflection and crack width.
In GFRP.
One more example.
Eventually, we have to go through this exercise in parallel to steel, to convince people. But eventually that may happen. Meaning once you gain enough confidence, you run 20 designs, every design is a failure in controlled in terms of deflection and crack width, then you forget about the load part of it and only focus on it may come to that, Anybody from online?
Anybody? Can we allow bundled bars in non-construction using FR?
Again, they said no for now because there is no data on bundled bars. For now. No, I said concrete people are wonderful with a lot of design insights and what have you, which is true. But at the same time, they're very restrictive because they don't have a mathematical approach to hang their hat onto. They always fall back on experimental data.
So in RCC concretes, there is much flexibility in choosing the diameters. Like if you're talking about the area of steel methodology, we can choose any diameter.
How big a bar you go to in steel?
What's your limit?
18, 22? I heard you have a bar number 22, like almost close to 2 inches. 20 or 20?
Maximum
32 mm is the largest.
32 mm.
Yes.
Okay, that is 10. Yeah, that is 10. 36 is 12. But actually FRP has it now up to 10 or even 12 they have in the code.
40 mm, up to 40 mm.
That may be in steel, not in FRP. Oh, there is? Oh, maybe your code. Oh, okay. Yeah.
Is it better to provide smaller diameter bars of large number than the large diameter bars of smaller number?
From the bond point of view.
Obvious that smaller diameter bars of large numbers will give you, assuming you satisfy the spacing requirements or whatever, assuming that smaller ones of large numbers will give you a much better bond.
Is the shear lag can be more in FRP bars?
Any way you cut it, the shear lag would be low, the bond strength will be high with smaller diameter bars. That's the way to go. But will you be able to satisfy the spacing requirements? It's always one thing or the other. It's a balancing act.
So is there any limitation of the percentage of reinforcement in any?
Of course. I told you 8% for columns, 4 or 5% or 6% for beams. 4% I think.
Indian code it is 4%.
Yeah, same with us too. Yeah. You don't want to exceed that kind of. Unless we come up with a better definition of how the compression GFRP controls, otherwise we will never be able to make a doubly reinforced beam and what max percentage you are talking about. All these cannot be well defined without
Analysis of compression.
compression side. Exactly.
Can we provide two different types of FRP bars in a macro? Like GFRP bar and CFRP bar. CFRP will have more stiffness. We can
Hybrid reinforcement.
Well, the hybrid systems, like I said, have certain limitations for the time, unless we overcome. I heard Professor Prakash wants to do some hybrid stuff.
My column I was.
Yeah. Then he understood when I was talking because of the incompatibilities that might lead to other issues, They're not accepting all composite, forget about the hybrid bars, you know.
If the thermal conditions are kept constant, then if we have like
Sure, absolutely. If the thermal conditions are constant, for example, meaning there is no freeze-thaw type effect, you know, or for that matter, if the freeze-thaw effects are not there, your crack growth or shrinking may be minimal, then you may not have as much of a problem even with steel. Look at it that way. Maybe different if you're wanting to use fresh water or seawater, keeping that component aside, but we are really pushing for seawater usage, sea sand usage. So then right off the bat, your sand mafia will be gone, right?
Yeah, there too.
Let us meet tomorrow instead of today. Are you leaving here today? You're here tomorrow. Yeah, let's meet tomorrow. Okay, they want a couple of people coming from. Yeah. I'm getting one guy from Cochin right now.
Okay, sir.
Yeah.
Sir, these are the materials we are using for GPC, geopolymer. But we have water content.
You may have water. We are not putting water.
Yes,
Let
sir.
me leave it there.
Can I get your combination in some?
Oh, sure, absolutely. When I go, send me an email or ask them.
Yesterday you.
Yeah, that one. So if you send me that, we are not using any water, geopolymer. What kind of, are you using a super plasticizer?
No, sir. In this, we not used any.
Yeah, sodium sulfate, sodium oxide, hydroxide. Yeah, I see
It's
that.
the latest.